What if I told you that right now, as you sit watching this, the very space between you and everything else in the universe is slowly, silently stretching? It's not something you can see or feel, but it's happening all around us, an invisible force gently pulling the cosmos apart, thread by thread, moment by moment. This isn't some abstract idea tucked away in a physics textbook. It's real, it's measurable, and it's one of the most profound truths about the universe we call home. Picture this: you wake up one morning and something feels off. The walls of your room seem a little farther apart than they were last night. The street outside looks wider. The sun in the sky appears dimmer, more distant. Even the atoms in your own hands feel like they're being gently tugged in every direction. It sounds like a scene from a dream or a science fiction story, but it's not. This is cosmic expansion, the silent, relentless stretching of spacetime itself, and while we don't feel it in our everyday lives, its effects ripple across the universe, shaping galaxies, bending light, and even determining the ultimate fate of everything that exists. In this video, we're going to do more than just talk about expansion. We're going to experience it together through a thought experiment, a journey of imagination and science that asks one simple but staggering question: what would it actually feel like to live in a stretching cosmos? We'll dive into the mysteries of dark energy, the hidden force accelerating this expansion. We'll explore how light travels across an ever-widening universe, how time itself is stretched and warped, and what it means for us tiny, conscious beings living on a small planet in a vast, growing sea of spacetime. This is about more than equations or distant stars. It's about reimagining reality itself. So settle in, open your mind, and let's begin. To truly grasp this idea, we need to let go of a very intuitive picture. We often imagine the universe as a vast, static stage, with galaxies simply moving across it like actors. But that stage isn't static at all. It's more like the surface of a balloon that's being steadily inflated. If you take a marker and put dots all over a deflated balloon, then start blowing it up, you'll see something remarkable. Every single dot starts moving away from every other dot. There's no center on that surface. No dot is special. From the perspective of any dot, all the others are receding. That is the essence of cosmic expansion. It's not that galaxies are rocketing away from some central point in a pre-existing space. It's that the very fabric of space itself is stretching, carrying the galaxies along with it. This isn't just a poetic metaphor. It's a measurable reality quantified by what we call the Hubble-LeMaitre law. In the 1920s, astronomers like Edwin Hubble and Georges LeMaitre made a stunning discovery. They found that the light from distant galaxies is shifted toward the red end of the spectrum, and the farther away a galaxy is, the greater this redshift becomes. This relationship between distance and recession velocity is a cornerstone of modern cosmology. It tells us that for every million parsecs of distance, a galaxy moves away from us about 70 kilometers faster every second. But crucially, that velocity isn't from a galaxy speeding through space like a bullet. It's the result of new space relentlessly blooming between us and that galaxy, stretching the wavelength of its light and making it appear to recede. Another wonderful way to visualize this is with a loaf of raisin bread baking in the oven. Think of the dough as the fabric of space-time and the raisins as galaxies. As the dough rises and expands, every raisin moves away from every other raisin. A raisin on one side of the loaf sees all other raisins moving away, and from any raisin's viewpoint, the same thing is happening. The expansion is uniform. This uniformity is a key feature on the largest scales. In every direction we look, and from every point in the universe, the expansion appears roughly the same. There is no center and no edge to this expansion. It's a property of the cosmos itself. However, this doesn't mean everything is being ripped apart. On smaller scales, the powerful force of gravity acts as cosmic glue, holding things together. Our Milky Way galaxy isn't expanding. The solar system isn't expanding. You are not expanding. The gravitational bonds between stars in a galaxy, between planets and their star, and between the atoms in your body are all far stronger than the gentle, large-scale tug of expansion. It's only in the vast, empty voids between galaxy clusters where gravity's pull is weak that expansion truly dominates and plays out unimpeded. And perhaps the most astonishing twist in this story is that this expansion isn't just happening, it's speeding up. Observations of distant supernovae in the late 1990s revealed that the universe's expansion is accelerating. Some mysterious repulsive force, which we call dark energy, is overcoming gravity's pull and pushing the cosmos apart at an ever-increasing rate. This discovery turned our understanding on its head and introduced one of the greatest mysteries in all of science. We're living in a universe that is not only stretching but doing so faster and faster with each passing moment. Now, to fully appreciate this mind-bending reality, we have to rewind the cosmic clock and step into the shoes of the brilliant, persistent astronomers who first uncovered it. For most of human history, the universe was considered static and eternal. Even Albert Einstein, when he formulated his theory of general relativity, was so convinced of a static universe that he introduced a cosmological constant, a fudge factor, really, into his equations to keep it from either collapsing or expanding. It would be a series of meticulous observations and a daring theoretical leap that would shatter this ancient belief. The first clues came from an unassuming astronomer at the Lowell Observatory named Vesto Slipher. Around 1912, Slipher was painstakingly studying the light from what were then called spiral nebulae, fuzzy patches in the sky whose nature was a complete mystery. By passing their light through a spectrograph which splits light into its constituent colors like a rainbow, he made an astounding discovery. For most of these nebulae, the familiar patterns of spectral lines were shifted toward the red end of the spectrum. This redshift indicated that these objects were moving away from us, and at staggering speeds far greater than anything seen within our own galaxy. Slipher had, without fully realizing it, found the first evidence of the cosmic recession. He was measuring the Doppler effect for light, but the implications were far grander than anyone could have imagined. The baton was then picked up by Edwin Hubble, working with the powerful new 100-inch Hooker telescope at Mount Wilson. Hubble had a crucial advantage. He was able to identify individual stars within some of these nebulae, specifically a type called Cepheid variables. These stars have a magical property. Their intrinsic brightness is directly tied to their pulsation period. By measuring how long it took for a Cepheid to brighten and dim, Hubble could calculate its true luminosity. By comparing that to how dim it appeared from Earth, he could then calculate its distance with remarkable accuracy. This allowed him to confirm something monumental. These spiral nebulae were not part of our Milky Way. They were entire island universes, themselves galaxies far beyond our own, separated by unimaginable gulfs of space. Hubble then performed the masterstroke. He combined his distance measurements for these galaxies with the velocity measurements from Slipher's redshifts. In 1929, he published a landmark paper showing a clear, direct correlation. The farther away a galaxy was, the faster it appeared to be receding from us. This relationship, now enshrined as the Hubble-LeMaitre law, was the smoking gun. The universe was not static, it was expanding. But there was another key figure in this story, a man whose contribution was initially overshadowed. Georges LeMaitre was a Belgian priest and physicist, working independently from Einstein's equations of general relativity. LeMaitre had already derived a theoretical model of an expanding universe in 1927, 2 years before Hubble's famous paper. He even derived a similar expansion rate relationship. He described a universe bursting forth from a primeval atom, a concept that would later become the Big Bang theory. When he presented his ideas, they were met with skepticism. The idea of a beginning to the universe was too radical for many. Even Einstein reportedly told LeMaitre, "Your calculations are correct, but your physics is abominable." History, of course, would prove LeMaitre right, and his theoretical work provided the crucial framework to understand what Hubble and Slipher were observing. It wasn't just that galaxies were flying apart, space itself was growing. This collective effort completely overturned centuries of belief. The static, eternal cosmos was gone, replaced by a dynamic, evolving, and breathtakingly large universe with a definite history and a beginning. Edwin Hubble captured the awe of this new perspective when he wrote about the realm of the nebulae, a realm whose very laws were written in the subtle redshift of starlight. These pioneers gifted us a new cosmic story, one where we are not in a fixed celestial sphere but riders on a vast, expanding fabric of spacetime. So how do we actually know the universe is stretching? The answer lies in a subtle but profound property of light itself, a cosmic fingerprint left on the light from distant galaxies that tells us they are moving away. This phenomenon is called redshift. To understand it, let's start with something familiar: sound. You've likely heard the pitch of a siren change as an ambulance speeds past you. As it approaches, the sound waves are compressed, making the pitch higher. As it moves away, the waves are stretched out, making the pitch lower. This is the Doppler effect, and it works for light too. When a source of light is moving toward us, its light waves get bunched up, shifting them toward the blue end of the spectrum. When it moves away, the waves are stretched, shifting them toward the red end. For decades, astronomers assumed the redshift from galaxies was simply this same Doppler effect on a grand scale, indicating they were flying through space away from us. But with the discovery of the expanding universe, we realized something far more mind-bending was happening. The redshift we see from distant galaxies isn't just from them moving through space. It's primarily from the expansion of space itself. This is a crucial distinction. Imagine you have a wave painted on a stretchy rubber sheet. If you pull on the edges of that sheet, stretching it, the wave itself gets longer. The wave isn't moving across the sheet is elongating, and the wave is simply along for the ride. This is exactly what happens to light as it travels across the expanding cosmos. A photon of light emitted by a distant galaxy billions of years ago has been traveling through space all this time, but the space it has been traveling through has been stretching relentlessly during its entire multi-billion-year journey. This cosmic stretching elongates the photon's wavelength, literally reddening it by the time it finally reaches our telescopes. The greater the distance the light has traveled, the more space has expanded beneath its feet, and the more extreme its redshift becomes. This is why redshift is our most powerful tool for measuring not just velocity, but cosmic distance and the history of expansion itself. To measure this, astronomers use an incredible instrument called a spectrograph. Attached to a powerful telescope, it acts like a cosmic prism, splitting the faint light from a far-off galaxy into a full rainbow spectrum. Within that spectrum are specific, dark lines, like a unique barcode caused by elements in the galaxy's stars, such as hydrogen or calcium, absorbing light at very specific wavelengths. We know what that barcode is supposed to look like from experiments in labs here on Earth. But when we look at the light from a distant galaxy, we find that its entire barcode has been shifted, lock, stock, and barrel toward the red end. By measuring precisely how far those familiar lines have been displaced, we can calculate the exact amount of redshift, which we denote with the letter Z. A small redshift means a relatively nearby galaxy. A large redshift means an immensely distant one, whose light has been stretched by a vast amount of expanding space. Some of the most extreme examples of this are quasars. These are incredibly bright, active cores of galaxies, powered by supermassive black holes, and they can be seen from the very edge of the observable universe. The light from some quasars exhibits such tremendous redshift that it tells us we are seeing them as they were when the universe was less than a tenth of its current age. Their light, which was originally emitted as visible or even ultraviolet light, has been stretched so dramatically by the expansion of space during its long journey that it arrives at our telescopes as infrared radiation. Without understanding cosmological redshift, we would have no way to interpret these faint, reddened signals as the brilliant beacons of the early universe that they truly are. It is this precise, measurable stretching of light that transforms redshift from a curious abstract concept into the definitive, observable evidence that we live in a dynamic, expanding cosmos. So if redshift is the observable effect, what is the actual physical mechanism causing it? To answer that, we need to move beyond analogy and into the heart of how general relativity describes our universe. The key is something called the metric, a mathematical formula that acts like a cosmic rulebook, telling us how to measure distances in the fabric of space-time. For an expanding universe that, on the largest scales, looks the same in every direction and from every point, this rulebook is known as the Friedmann-LeMaitre-Albertson-Walker metric. It's a mouthful named after the physicists who derived it, but its message is profound. It's the mathematical blueprint for a homogeneous and isotropic universe, one that is smooth and uniform in its grand design, exactly what our telescopes observe. At the core of this metric is a single, powerful number called the scale factor. Think of the scale factor as the master control dial for the entire universe. It's usually denoted by the symbol A of T, emphasizing that it changes with time. When the universe was young and dense, the scale factor was small. As the universe expands, the scale factor increases. This number doesn't just represent expansion in a vague sense. It literally multiplies all distances. Imagine two galaxies floating in space. The true physical distance between them isn't fixed. It's equal to their coordinate distance, a kind of fixed address on the cosmic grid multiplied by this ever-growing scale factor. The galaxies aren't engines roaring away from each other. They are like two friends standing still on opposite ends of a stretching rubber band. Their coordinates haven't changed, but the real space between them is growing because the universe's scale factor is getting larger. This leads to perhaps the most counterintuitive idea in all of cosmology. Two objects can be completely at rest with respect to the expanding space around them, what cosmologists call comoving with the expansion, and yet the distance between them will still increase. They are not moving through space. Space itself is evolving, carrying them apart. This is the pure, elegant essence of metric expansion. The Hubble-LeMaitre law we discussed earlier flows directly from this idea. The recession velocity of a distant galaxy isn't a traditional velocity at all. It's more accurately called a recession rate. It is the rate at which new space is being created between us and that galaxy. This rate is given by what we call the Hubble parameter, h, which is essentially the current growth rate of that universal scale factor. We can even put a number on this rate today. The current value of the Hubble parameter, known as the Hubble constant, is about 70 kilometers per second per megaparsec. Now, let's unpack what that actually means. A megaparsec is an astronomically huge distance, roughly 3.26 million light-years. So, this value tells us that for every additional megaparsec of distance between two galaxies, the space between them is stretching at a rate of 70 kilometers every second. It sounds fast, but its effect is incredibly subtle on human scales. The distance from the Milky Way to the Andromeda Galaxy is about 0.77 megaparsecs. This expansion would predict they should be drifting apart at about 54 kilometers per second. But they are not. They are actually moving toward each other at a much higher speed because their local gravitational attraction completely overwhelms the gentle background drift of expansion. This only changes when you look at truly colossal distances where the cumulative effect of all that stretching space becomes dominant. This mathematical framework is the very foundation of the Big Bang cosmology. By plugging different ingredients into the equations like matter, radiation, and dark energy, we can rewind the scale factor back in time. As R of T gets smaller and smaller, the universe gets hotter and denser, all the way back to an initial state of incredible density. We can also run the equations forward to predict the universe's ultimate fate. Will the scale factor continue to increase forever? Will it eventually slow down or even reverse? The answers depend on the precise composition of the cosmos, which is why measuring the exact density of matter and the nature of dark energy is one of the most active pursuits in modern science. This isn't just abstract math. It's a time machine and a crystal ball built from the language of geometry and physics, allowing us to trace the grand narrative of the cosmos from its fiery beginning to its distant, uncertain future. For most of the 20th century, cosmologists were convinced they understood the basic fate of the universe. The gravitational pull of all the matter in the cosmos was acting like a cosmic brake, gradually slowing down the expansion that began with the Big Bang. The only real question was whether there was enough matter to eventually halt the expansion and pull everything back in a big crunch, or if the universe would just keep expanding forever at an ever-decreasing rate, coasting toward a quiet, cold fade out. Then, in 1998, two independent teams of astronomers made a discovery so shocking it turned this entire narrative on its head. They found that the expansion of the universe isn't slowing down at all. It's speeding up. Something was overcoming the relentless pull of gravity and giving the cosmos a powerful push outward. That something, whatever it is, we call dark energy. The key to this discovery was a specific type of cosmic explosion, a Type 1, a supernova. These are thermonuclear blasts that occur when a white dwarf star steals just enough matter from a companion to tip it over a critical mass threshold. The beautiful thing about these explosions is that they are remarkably consistent. They all reach nearly the same peak brightness. This makes them what astronomers call standard candles. If you know how bright something truly is, and you measure how dim it appears from Earth, you can calculate its distance with incredible precision. The two teams, the Supernova Cosmology project led by Saul Perlmutter, and the High Z Supernova Search team led by Brian Schmidt and Adam Rees, were using these stellar explosions to measure distances to galaxies billions of light-years away. By combining these distances with measurements of the supernova's redshifts, they were mapping out the expansion history of the universe. They expected to see that the more distant supernova, those that exploded when the universe was younger, were receding faster than the standard model predicted, a sign that expansion was decelerating over time. Instead, they found the exact opposite. The distant supernova were significantly dimmer than they should have been. This could only mean one thing: they were farther away than anyone had calculated. The only explanation was that in the past, the universe was expanding more slowly than it is today. The expansion rate has been increasing. It was as if you threw a ball into the air, and instead of slowing down as gravity pulled on it, it shot away from you faster and faster into the sky. The results were so bizarre that the team spent years checking and rechecking their work, desperately searching for some mundane error, dust obscuring the light, evolution in the supernova themselves, anything. But the data held firm. The universe's expansion is accelerating. The discovery was awarded the Nobel Prize in Physics in 2011, a testament to its earth-shattering importance. As Adam Rees later recalled, the feeling was one of both terror and excitement, realizing they were seeing something that fundamentally challenged our understanding of physics. So what is this mysterious dark energy that's causing this acceleration? The simplest and currently leading explanation comes straight from Albert Einstein, though he himself considered it his biggest blunder. It's the cosmological constant. Originally, Einstein introduced this constant, represented by the Greek letter lambda, into his equations of general relativity to force the universe to be static, which was the prevailing belief at the time. After Hubble's discovery of expansion, Einstein discarded the idea, but modern cosmology has brought it back with a vengeance. In this context, the cosmological constant is conceived as a property of space itself. Empty space is not nothing. According to quantum physics, it's a seething, bubbling foam of virtual particles popping in and out of existence. This vacuum energy is thought to exert a negative pressure, a kind of tension that causes space to expand. And because it's a property of space, the more space there is, the more of this repulsive energy there is. This creates a runaway feedback loop. Expansion creates more space, which creates more dark energy, which causes faster expansion, and so on. It behaves exactly like a spring, but one that pushes outwards instead of pulling in. The numbers involved are almost incomprehensible. Based on precise measurements from the cosmic microwave background and other probes, we now know that dark energy makes up about 68% of the total energy density of the universe. All the stars, planets, galaxies, gas, and dust, everything we can see and touch and measure comprises less than 5%. The rest is another mysterious component, dark matter. This means the dominant force shaping the overall evolution of our cosmos is this completely invisible, repulsive energy we barely understand. It's a humbling realization. Alternative theories exist, such as quintessence, which proposes that dark energy is a dynamic field that varies over time and space, unlike the constant lambda. But so far, the cosmological constant remains the model that best fits the data, even if its underlying physical origin remains one of the greatest mysteries in all of science. The profound puzzle, and the reason dark energy continues to drive so much cutting-edge research, is the staggering discrepancy between the predicted value of the cosmological constant from quantum theory and the value we actually observe from astronomy. The theoretical predictions are too large by a factor of 10 to the power of 120. That's a 1 followed by 120 zeros. It is arguably the worst prediction in the history of physics. This cosmological constant problem tells us that we are missing something absolutely fundamental in our understanding of how gravity and quantum mechanics fit together. As physicist Lawrence Krauss has put it, dark energy is either the most boring thing in the universe or the most interesting. It could be a simple constant of nature, an inherent property of the vacuum. Or it could be a signpost pointing toward a completely new theory of physics, a revolution waiting to happen. This enigma ensures that the study of dark energy remains at the very forefront of cosmology, with major new telescopes and space missions being designed for the sole purpose of unraveling its secrets and determining the ultimate fate of our accelerating universe. So we arrive at the heart of our journey, the central question that transforms this from a lecture into an experience. What would it actually feel like if you could somehow mute the roar of gravity, silence the electromagnetic buzz holding your atoms together, and tune your senses to perceive the silent, background hum of the universe itself expanding? What sensation would wash over you? The first thing to understand is why this is purely a thought experiment. In our reality, you don't wake up feeling taller because the space between your atoms expanded overnight. The forces that bind you together, the same forces that hold planets in orbit and galaxies in their majestic swirls, are unimaginably stronger than the gentle, large-scale tug of cosmic expansion. It's like trying to hear a single, quiet violin note while standing next to a roaring jet engine. The engine of local physics drowns out the faint cosmic music completely. The Hubble constant, that rate of 70 kilometers per second per megaparsec, translates to an effect so minuscule on human scales it's utterly negligible. Over the entire diameter of Earth, expansion adds less than 1/10 of a millimeter of new space every second, an amount instantly overcome by the powerful bonds of gravity and atomic forces. So we are mercifully and literally held together. But the power of a thought experiment is that we can change the rules to isolate a single phenomenon. So let's construct a new reality. Imagine a universe where the fundamental forces gravity, electromagnetism, the strong and weak nuclear forces are suddenly, magically switched off. All that remains is the pure, unopposed expansion of space itself. In this silent, frictionless void, what happens? Picture yourself floating in this emptiness with a single, perfectly still friend a few meters away. You are both completely at rest. There is no push, no pull, no motion between you. You blink, and in that moment you notice something imperceptibly different. The space between you has grown, not because you moved and not because your friend moved. The very grid of reality upon which you are both fixed points has itself stretched. You are now slightly farther apart. It's not a motion you can feel in your stomach like acceleration. It's a geometric change, a quiet recalibration of the universe. You look at your friend's face and it appears ever so slightly smaller. The features a tiny bit less distinct, as if viewed through a lens that is slowly, constantly zooming out. Now let this process continue. With every passing second, the gap widens. The silence is absolute, broken only by this eerie, relentless distancing. You shout, but the sound waves themselves are stretched as they travel through the expanding medium between you, their wavelengths lengthened, their pitch dropping into a deep, drawn-out rumble that never quite reaches your friend. If you could see the light from their body, it would be reddening, shifting toward the infrared, a fading ember in the growing dark. There is no wind on your face, no force acting upon you. The experience is one of profound and passive isolation. You are a spectator to your own dissolution, watching the rest of the cosmos recede as if you were the still center of a swelling, silent bubble. It's a feeling of deep, existential unease. The universe itself is the medium, and it is flowing away from you in all directions. This is the essence of metric expansion, made personal. It's not about being pushed, it's about being connected to everything else by a fabric that is relentlessly growing, elongating every possible path between any 2 points. In our imaginary universe, this would eventually dissolve everything. Solar systems would unbind, planets would drift from their stars, and eventually, the very molecules and atoms that make up matter would find the space between their particles growing too vast for their bonds to handle. Everything would gently, silently, and irreversibly come apart at the seams. This thought experiment strips expansion down to its purest form, allowing us to viscerally grasp the powerful, underlying current that shapes the cosmos on the grandest of stages, even as we are thankfully anchored against its pull in our local corner of reality. It's a question that naturally arises from all this talk of a stretching cosmos. If the universe is truly expanding, why can't we feel it? Why doesn't the ground beneath our feet seem to grow? Why don't we see our coffee cups drifting slowly away from us on the kitchen table? The answer lies in the sheer scale of the effect and the incredible strength of the forces that hold our everyday world together. Cosmic expansion is real and powerful on the grandest stages, but here in our local neighborhood, it is utterly dwarfed, like a gentle breeze trying to topple a mountain. Let's put some numbers to this. The current rate of expansion is captured by the Hubble constant, approximately 70 kilometers per second per megaparsec. A megaparsec is an almost unimaginable distance, about 3.26 million light-years. So, this rate means that for every megaparsec of distance between two objects, the space between them grows by 70 kilometers every single second. That sounds dramatic, but we need to translate that to a human scale to see why it's imperceptible. Consider the distance from the Earth to the Sun, which is about 1 astronomical unit, or 150 million kilometers. Over that entire vast distance, the expansion of space adds a minuscule amount of new space each second, roughly 1/10 of a millimeter. That's about the width of a human hair. And that's over 93 million miles. The expansion happening within the space occupied by your own body is so infinitesimally small that it has no physical consequence whatsoever. This is because the forces that govern our local reality are phenomenally stronger than this background hum of expansion. The electromagnetic force that binds atoms together into molecules and molecules into the chair you're sitting on is overwhelmingly powerful on its own scale. The chemical bonds holding your body together would need to be stretched by a factor vastly greater than the universe's expansion rate to ever break. It's not even a contest. Gravity, which seems weak compared to the other forces, is still the dominant master of celestial mechanics on the scale of solar systems and galaxies. Its relentless pull keeps planets in stable orbits around stars and keeps stars orbiting within galaxies. The Milky Way and the Andromeda Galaxy, for instance, are not being pushed apart by expansion. They are locked in a gravitational dance, actually moving toward each other and destined to collide in a few billion years. Expansion only wins the tug of war in the vast, empty deserts of space between galaxy clusters, where gravity's grip is too weak to counteract the cumulative stretching of space over such immense distances. A perfect analogy is our planet's rotation. The Earth is spinning at a furious pace over 1,000 miles per hour at the equator, yet we don't feel this incredible velocity. We don't feel a constant, roaring wind on our faces or get thrown off into space. Why? Because we are moving with the Earth, and the scale of the motion is so large and uniform that our senses, attuned to local changes and relative movements, simply don't register it. The force of gravity pins us to the surface, making the entire system feel stationary from our perspective. In the same way, we are commoving with the expansion of the universe. We are embedded within the stretching fabric, and the local forces that structure our existence are so dominant that they completely mask the subtle, large-scale evolution of space itself. This creates a profound illusion of stillness. From our limited vantage point, the universe appears static and fixed. The stars seem like permanent fixtures in the sky, and the dimensions of our rooms feel constant. But this is a local truth, not a cosmic one. It's a testament to the fact that the laws of physics operate on multiple scales. The rules that govern the behavior of quarks and atoms are not the same rules that govern the evolution of the cosmos over billions of years. We are protected from the grand dynamics of the universe by the very same forces that give our lives structure and stability. The expansion is always there, a silent, relentless background process, but to perceive it, we must train our telescopes on the deepest reaches of space and time, looking for the faint, reddened light of galaxies being carried away from us on the irresistible current of expanding space. Now let's push this thought experiment to its absolute limit. Let's imagine a universe where the cosmic dials have been twisted and we can isolate a single force. In this hypothetical reality, we switch off gravity, not just the Earth's pull, but the entire gravitational force, the attraction between every particle, every planet, every star. We silence the great cosmic architect that builds galaxies and binds solar systems. What we are left with is the pure, unadulterated, and relentless expansion of space itself, operating without any opposition. In this silent, frictionless void, the true, raw power of the Hubble flow is unleashed, and the result is both beautiful and terrifying. At first, the change would be imperceptible. You'd be floating in space, perhaps watching a familiar planet hanging in the blackness nearby. But then, you'd notice it beginning to drift, not with a jerk or a push, but with a smooth, geometric inevitability. The space between you and that planet is not just empty volume, it is an active participant, constantly generating more of itself. The planet would appear to recede, slowly at first, then with gathering momentum, like a ship caught on an outgoing tide it cannot fight. This isn't a trajectory or an orbit, it is a fundamental recalibration of distance itself. Every second, the gap widens because the fabric that defines the gap is stretching. This same process would unfold everywhere at every scale. On the grandest level, entire galaxy clusters, once held in a delicate gravitational balance, would simply relax. They would dissolve, their member galaxies drifting apart in a silent, cosmic dispersal. Each galaxy itself would begin to unravel. Stars that once traced elegant orbits around a galactic center would instead travel on straight-line paths, moving away from each other as the space within the galaxy itself expanded. The beautiful spiral arms, sculpted by gravity over billions of years, would slowly smear out into a featureless, expanding cloud of stars. Zoom in further, and the dissolution becomes even more profound. Within a solar system, planets would drift from their star. The Earth would slowly leave the Sun behind, moving into an ever colder and darker isolation. The Moon would drift from the Earth. There would be no more orbits, no more years, no more days, just an endless, increasing separation. The very concept of a system would lose all meaning. There are no bonds, only distances that are forever growing. But the most unsettling unraveling would happen at the very smallest scales. The forces that hold matter together, the electromagnetic force binding atoms into molecules and the strong nuclear force binding atomic nuclei, are not gravity. In our thought experiment, we've only turned off gravity, so you might think a rock would still be a rock, or a person would still hold their shape. But here's the deeply counterintuitive twist. The expansion of space doesn't discriminate. It acts on all distances. The space between the Sun and the Earth expands. The space between your hand and your coffee cup expands. And critically, the space between the atoms that make up your hand and the atoms that make up that cup also expands. Given enough time, even the mighty electromagnetic bonds holding molecules together would be tested. The space between individual atoms in a molecule would be stretching. It would be an impossibly slow process, but in a universe with no other forces to counteract it, it would be relentless. Eventually, even molecules would be stretched apart. Matter itself would cease to be stable. Solids, liquids, and gases would all gradually dissipate into a diffuse, ever-thinning haze of fundamental particles. each one drifting away from every other one on a sea of stretching space. It would be the ultimate silence, a universe where no structure, no complexity, and no life could ever form or be maintained. Everything would be smoothed out into a perfect, featureless, and lonely uniformity. This stark scenario is more than just a flight of fancy. It's a powerful tool used in cosmology to understand the precise role that different forces play in shaping our universe. By imagining a world without gravity, we gain a profound appreciation for the fact that our reality is a cosmic tug of war. On one side, there's the structuring, collecting, building force of gravity. On the other, the smoothing, dispersing, stretching force of expansion. Our actual, beautiful, and complex universe exists in the dynamic tension between these two fundamental tendencies. Gravity won the battle locally, giving us galaxies, stars, planets, and us. But on the largest scales, in the voids between the great cosmic filaments, expansion is winning, pushing the universe toward an increasingly diffuse future. This leads to a haunting, almost philosophical question. If a universe governed solely by expansion allows for no stable structures, then it allows for no planets, no chemistry, and certainly no observers. What would it be like to be conscious in such a place? It's a paradox. Consciousness seems to require complexity, a structured brain made of structured molecules, operating in a structured environment. A purely expanding universe offers none of that. It is a cosmos that is not only hostile to life, but fundamentally incompatible with the very concept of an observer. There would be no one to watch the galaxies drift apart, no one to feel the eerie solitude. The universe would expand in perfect, uninterrupted silence, utterly alone and utterly unaware of itself. This thought experiment doesn't just show us what expansion does. It reveals the critical, foundational role that gravity plays in creating a universe that can actually be lived in and wondered about. This grand, uniform drift of galaxies, carried along by the expansion of space itself, is what cosmologists call the Hubble flow. It's the cosmic baseline, the quiet, underlying current upon which the entire universe is gliding. Imagine a vast, placid river flowing through an endless landscape. Floating on its surface are countless leaves, each one a galaxy. The river isn't flowing to anywhere. The river itself is simply widening, and as it does, every leaf naturally drifts away from every other leaf. There are no rapids, no whirlpools, just this smooth, relentless, and orderly expansion. This is the Hubble flow. The motion of galaxies that are simply commoving with the expansion of the universe, their recession dictated precisely by the Hubble-LeMaitre law. But our cosmic river is not perfectly smooth. Upon this fundamental current, other motions are superimposed. Just as a leaf might be caught in a small eddy or tugged by a passing fish while still being carried by the river's main flow, galaxies can have their own local, peculiar motions. These are deviations from the pure Hubble flow, almost always caused by the relentless pull of gravity. Within galaxy clusters, like our own local group which contains the Milky Way and Andromeda, gravity is the dominant force. Andromeda isn't receding from us in the Hubble flow. It's actually blue shifted, hurtling toward us at over 100 kilometers per second, because our mutual gravitational attraction has completely overcome the background expansion. We are in a gravitational eddy, a swirling dance that will eventually lead to a colossal merger, all while our entire local group is carried together within the larger Hubble flow. Astronomers can actually map this intricate dance by meticulously measuring both the distance and the redshift of thousands of galaxies. They can calculate what a galaxy's velocity should be if it were perfectly following the Hubble flow. They then compare this predicted velocity to the velocity they actually observe. The difference is the galaxy's peculiar velocity, its own individual motion atop the cosmic river. These peculiar velocities tell a vivid story. They reveal the hidden architecture of the cosmos, mapping out immense gravitational structures. Galaxies are seen flowing toward dense regions like the Virgo cluster, or being pulled by the gravitational behemoth known as the Great Attractor. These motions allow scientists to create three-dimensional maps of the cosmos's mass distribution, inferring the presence of vast amounts of dark matter that tug on the visible galaxies. Tools like massive Redshift surveys projects such as the Sloan Digital Sky Survey have been instrumental in painting this picture. By collecting the spectra for millions of galaxies, these surveys don't just show us where galaxies are, they show us how they are moving. The resulting maps are breathtaking, revealing a cosmic web of filaments and voids, with galaxies streaming along invisible rivers of gravity, all while the underlying Hubble flow continues its steady, uniform expansion. This beautiful complexity, the smooth background flow combined with the swirling, local motions, is the complete kinematic story of our universe. It shows us a cosmos that is both orderly in its grand design and dynamically messy in its local details, a place where the largest forces are elegantly simple, while the interactions they create are wonderfully complex. But this stretching of space does far more than just push galaxies apart and redden their light. It reaches into the very fabric of time itself, warping our perception of duration and history in ways that are just as profound. To understand this, we need to revisit one of Einstein's greatest insights, that space and time are not separate entities but woven together into a single, malleable fabric called spacetime. Just as the expansion of space stretches the wavelengths of light, it also stretches the very intervals of time for events happening in the distant, expanding cosmos. This leads to a phenomenon we can call cosmological time dilation. Think of it like this. Imagine you receive a series of timed signals from a distant spacecraft, each 1 minute apart. Now, imagine that the space between you and that spacecraft is expanding during the journey of those signals. The first signal leaves its source and begins traveling toward you. But as it travels, the space behind it is stretching, effectively making the distance it has to cover longer and longer. This doesn't just delay its arrival, it also means the gap between that first signal and the next 1 minute signal gets stretched out. By the time these pulses of light finally reach your telescope, the regular 1 minute intervals sent from the source have been dilated. They might arrive 2 minutes apart or 5 or even more, depending on how much the universe has expanded during their epic journey. The clock on that distant spacecraft, as seen by you, appears to be ticking agonizingly slowly. This isn't just a delay, it's a fundamental change in how we perceive the flow of time from distant regions. This effect has been directly observed in the light curves of ancient supernovae. Astronomers use a specific type of stellar explosion, a Type 1, a supernova, as a standard candle because they all tend to follow a very predictable pattern of brightening and fading. It's a recognizable sequence like a familiar song, but when they look at these supernovae in extremely distant galaxies whose light has been traveling for billions of years, they see that the entire song is playing in slow motion. The rise to peak brightness takes longer. The gradual fade back to darkness is more drawn out. The entire event is temporally stretched, exactly as predicted by the expansion of the universe. The supernova isn't actually evolving more slowly in its own local frame of reference. From the perspective of someone right next to it, it would explode and fade in the standard amount of time. But from our vantage point billions of light years away, we are watching a recording of that event that has been slowed down by the relentless expansion of the space its light had to traverse. This time dilation is the temporal twin of cosmological redshift. if redshift stretches the light's wavelength, time dilation stretches the light's frequency, the rate at which the waves arrive. They are two sides of the same coin, both born from the stretching of spacetime. This creates a truly mind-bending consequence. When we look at the most distant galaxies, we are not just looking back in time. We are looking at a version of time that is itself distorted, flowing at a different rate than our own. The early universe, as we see it, appears to unfold in a kind of cosmic slow motion. The formation of the first stars and galaxies, which might have happened over millions of years in their own rest frame, appears to us to take even longer. It adds a layer of deep, almost philosophical complexity to our observations. We are not passive viewers of a cosmic movie. We are viewers watching that movie through a peculiar lens that stretches both the images and the scenes. This all flows directly from the equations of general relativity, which beautifully describe how matter and energy tell spacetime how to curve, and how that curved spacetime, in turn, tells matter and energy how to move. The expansion of the universe is the curvature of spacetime on the grandest possible scale. And just as a massive object like a black hole can warp time so severely that it appears to almost stop from a distant viewpoint, an effect called gravitational time dilation, the overall expansion of the universe imposes its own form of time warp across cosmological distances. It is a subtle but powerful reminder that there is no universal clock ticking away in the background. The rate at which time passes is relative, dependent on both gravity and motion, and as we now see, on the dynamic evolution of the cosmos itself. The expansion we've been exploring isn't just something happening in space and time. It is something that is actively reshaping the very stage of space-time upon which the cosmic drama plays out. Now let's turn our attention to the travelers, the messengers that bring us the story of the cosmos, photons of light. What happens to these tiny packets of energy as they embark on epic journeys across an ever-widening universe? Their voyage is not a simple straight-line trip through a static void. They are surfing a dynamic, stretching fabric of spacetime, and this journey fundamentally alters them, leaving an imprint that tells us everything about the history of expansion. Imagine a single photon, a particle of light, being emitted by a brilliantly hot star in a young galaxy billions of years ago. It bursts forth with a specific high energy, vibrating at a precise frequency, let's say it's blue light. It begins its long journey toward us, traveling at the ultimate speed, the speed of light. But as it travels, something subtle and relentless is happening. The very space through which it is moving is expanding. Think of the photon's wavelength, the physical distance between the peaks of its light wave, as being painted onto the fabric of spacetime itself. As that fabric stretches during the photon's multi-billion-year trip, the wavelength is stretched along with it. The wave is literally elongated. This stretching has a direct and profound effect. The energy of a photon is inversely proportional to its wavelength. The longer the wave, the lower its energy. So as the universe expands and the photon's wavelength is stretched, its energy steadily decreases. That once vibrant blue photon of light, after its long journey, arrives at our telescopes as a much redder, lower energy photon. This is the cosmological redshift in action, not as a simple Doppler shift from motion, but as a direct loss of energy imparted by the expanding universe itself. The light hasn't gotten tired from its long journey. It has been fundamentally cooled by the cosmic expansion, like a hot object cooling down as it's stretched thin. A powerful way to visualize this is to think of a message written on a rubber band with a perfect, crisp font. The rubber band represents a slice of space-time, and the message is a photon's wavelength. As you hold the ends of the rubber band and begin to stretch it, the letters of the message don't just move apart, they themselves become distorted, stretched out, and fainter. The information is still there, but its form has been fundamentally altered by the stretching of its medium. In exactly the same way, the light from distant galaxies carries information about its source, what elements are present, how hot the stars are, but that information is redshifted, stretched to longer, redder wavelengths by the expansion of space it had to traverse. This process of cosmic cooling is not just a curious effect on individual photons. It is the reason we can see the afterglow of the Big Bang itself. Rewind the clock about 13.8 billion years. The entire universe was an incredibly hot, dense, glowing plasma, so opaque that light couldn't travel freely. It was a searing, brilliant fog. Then, about 380,000 years after the Big Bang, the universe had expanded and cooled just enough for atoms to form, allowing light to finally decouple from matter and travel freely across space. In that moment, the entire cosmos was flooded with light and intense, blinding glow. Now follow the journey of those first photons. They have been traveling through the expanding universe ever since that moment of liberation. And for all that time, over nearly 14 billion years, the expanding space has been stretching their wavelengths, cooling their energy, and redshifting their light. The once searing visible and ultraviolet light has been stretched so dramatically that it now arrives at Earth as microwave radiation. We detect this as a faint, nearly uniform signal coming from every direction in the sky, the cosmic microwave background radiation. It is the oldest light we can see, the cooled remnant of the fireball of creation, and it is perhaps the most direct and powerful evidence we have for the expansion of the universe. That static on an old analog television, about 1% of that is literally the cooled down light from the birth of the cosmos, a fossilized echo of the Big Bang that has been stretched across the ages. This relentless redshifting and cooling of light also places a fundamental limit on our ability to communicate and observe across the cosmos. As the expansion continues to accelerate, driven by dark energy, there will come a point for any photon emitted today from a sufficiently distant galaxy that it will never reach us. The space between us and that galaxy will be expanding faster than the speed of light can traverse it. This doesn't violate relativity, as it is space itself that is expanding faster than light can cross it. Nothing is moving through space faster than light. But it means that the light and any information it carries is forever lost to us. The observable universe, the portion of the cosmos from which light has had time to reach us, is actually shrinking in terms of the number of galaxies we will be able to see in the far future. We are living in a privileged cosmic era where we can still see a vast fraction of the universe's history. Billions of years from now, observers in our galaxy will look out into a much darker, much emptier sky, their view of cosmic history having faded into darkness as the light from other galaxies is redshifted into oblivion and ultimately cut off by the accelerating expansion. The story carried by light has a final chapter, and the stretching cosmos is slowly turning the pages toward its conclusion. This idea of light being stretched and ultimately lost to the void brings us to a profound and humbling cosmic truth. There are fundamental limits to what we can ever see or know. The universe may be infinite, but our view of it is not. We are bounded by cosmic horizons, ultimate barriers set by the finite speed of light and the relentless, accelerating expansion of space itself. The most fundamental of these is the particle horizon. Think of it as the ultimate boundary of our observable universe. It's not a physical wall out in space, it's a limit in time. Because the universe is about 13.8 billion years old, light has only had 13.8 billion years to travel. This means we can only see objects whose light has had sufficient time to reach us since the Big Bang. Every point in the universe has its own particle horizon. a spherical volume that contains everything that could possibly be seen from that location. We are at the center of our own observable universe, just as an alien on a planet in a distant galaxy is at the center of theirs. Our particle horizon is the farthest we can look out into space, which is also the farthest we can look back in time, all the way to the faint glow of the cosmic microwave background, the very edge of visible creation. Now imagine you are an artist standing on the surface of a perfectly spherical, inflating balloon. You have a paintbrush that can only paint a line at a fixed speed, the speed of light. You start painting outward in every direction, but as your paint travels, the balloon itself is stretching, expanding the canvas beneath your brush. There will be distant regions of the balloon that your paint simply cannot reach because the surface is expanding faster than your paint can cover the new distance. Those regions are forever beyond your horizon. They are part of the balloon, but they are not and never will be part of the picture you can create. This is our situation with the particle horizon. We are forever separated from regions of the universe whose light is still in transit, and from those whose light will never reach us at all. But in an accelerating universe, there's an even more dramatic and final horizon at work, the cosmological event horizon. This is a concept that shares an eerie similarity with the event horizon of a black hole. In a universe dominated by dark energy and accelerating expansion, there comes a point for every distant galaxy where the space between us and it is expanding faster than the speed of light. When this happens, any light that galaxy emits from this moment onward will never, ever reach us. It will be trying to swim against a current that is flowing faster than it can swim. That galaxy has effectively passed beyond our event horizon. It hasn't vanished, it's still there. But any event happening there now is forever invisible to us. We are receiving its ancient history, light emitted billions of years ago, but its present and its future are permanently hidden from our view. This creates a strange and isolating cosmic fate. As the acceleration continues, more and more galaxies will be pulled beyond this event horizon. The observable universe will not only appear to shrink as galaxies redshift into invisibility, but the number of galaxies we can theoretically still receive new information from will actually decrease. We are living in a uniquely privileged era where we can still observe a vast number of galaxies and piece together a great deal of cosmic history. Civilizations that arise in our galaxy trillions of years in the future will look out into a profoundly dark sky. The evidence for the Big Bang, the cosmic microwave background, will have been redshifted into such long wavelengths it will be undetectable. The myriad galaxies we see today will have vanished from their view, their light forever lost beyond the event horizon. Their universe will consist of the merged remnants of the local group, a single, giant elliptical galaxy adrift in an immense and impenetrable blackness, with no clues to a larger, richer cosmic story. These horizons are not just abstract curiosities, they actively shape the entire enterprise of cosmology. They define the very data we have to work with. They tell us that our maps of the large-scale structure of the universe are not maps of the entire universe, but only of our observable patch. They force us to ask humbling questions. What lies beyond the particle horizon? Is the universe vastly larger than what we see, perhaps even infinite? Are there regions with completely different physical constants or laws of physics, forever separated from us by an uncrossable expanse? The existence of these horizons is a powerful reminder that our knowledge of the cosmos, while incredible, is ultimately finite. We are like sailors on a vast ocean who can only see to the curvature of the Earth, forever wondering what mysteries lie just over that invisible, receding line. So let's shift our perspective from the grand mechanics of the cosmos to something far more intimate, the inner experience of a conscious mind adrift in this ever-widening reality. We've explored the physics of isolation. Now let's feel its weight. Picture yourself as an astronomer in the far, far future, perhaps billions of years from now, living on a planet orbiting a long-lived star. Your civilization has a deep and ancient history of astronomy, with records stretching back to an our era, when the night sky was ablaze with the combined light of countless galaxies, a glittering tapestry that spoke of a vast and connected cosmos. But now you look up. The change has been imperceptibly slow over generations, but the records are clear. Where there were once thousands of visible galaxies, only a handful of the very closest remain. The rest haven't vanished, they have been erased by the expansion. Their light, stretched by the relentless growth of space, has redshifted to wavelengths too long for any eye to see, their photons now feeble whispers of radio waves lost in the silent static of the cosmos. The great cosmic web, once a brilliant network of light, has gone dark. You are living inside a shrinking island of visibility, and the shores of that island are receding faster every day. The psychological impact of this would be profound, a deep and abiding loneliness on a cosmic scale. It would be the ultimate FOMO, the fear of missing out applied to the entire universe. You would know from your ancestors' records that a spectacular reality exists, but it is a reality now forever beyond your perception. You are like the last person in a vast, darkening library, watching as the light in each aisle slowly extinguishes, knowing that countless stories are fading into unreadable darkness just beyond your reach. There is a haunting term for this eventual state, heat death, not just a thermal equilibrium but an informational one, a universe where knowledge of other realms becomes physically impossible to obtain. Use the metaphor of a lone sailor on an infinite ocean. In the beginning, your ship is part of a grand fleet, with countless other vessels visible on the horizon, their lights twinkling, a sense of community and shared journey. But a silent, powerful current begins to pull each ship apart. One by one, the lights on the horizon dim and vanish, not because they've sunk, but because the ocean between you has grown so vast that their light can no longer cross the gap. You find yourself utterly alone on a flat, black sea that stretches into infinity in every direction. You can shout, but your voice will never reach another soul. You can light a signal fire, but its glow will illuminate nothing but your own tiny, isolated deck. This is not just solitude, it is the crushing realization that the community of the cosmos is dissolving, and you are a witness to its quiet, desperate end. This scenario touches on deep philosophical questions about meaning and connection. For humans, much of our sense of purpose is derived from being part of something larger than ourselves. A family, a culture, a species, a planet. That sense of connection has, for centuries, expanded outward to include the cosmos. The famous astronomer Carl Sagan captured this beautifully when he said, "The cosmos is within us." We are made of star stuff. We are a way for the universe to know itself. But in an accelerating, isolating universe, that beautiful loop of self-knowledge is severed. If the universe can no longer know its own parts, does that diminish its meaning? Does it diminish ours? How would knowing that the universe is fundamentally drifting apart, that the very fabric of reality is ensuring our ultimate separation from everything else, affect our psychology? It could foster a profound existential angst, a feeling that all endeavors are ultimately futile because they will be lost to an impenetrable void, or it could have the opposite effect. Faced with such undeniable isolation, beings might turn an intense focus inward, cherishing their local connections with a ferocity and passion unknown before. Every relationship, every piece of art, every moment of joy on that single, isolated world could become infinitely more precious because it is all there is. The entire meaning of existence would have to be found not in the grand cosmic scale, but in the microscopic details of a single drifting point of light. This is the emotional core of the thought experiment. It forces us to ask what truly matters when the universe itself seems to be closing the curtains on the grand show, leaving us to find the spotlight within ourselves. These mind-bending concepts of metric expansion and redshift can feel incredibly abstract, so let's bring them back down to earth with some everyday comparisons. The human brain is wired to understand the world through analogy, and cosmology is no different. One of the most beloved and enduring analogies is that of the rising raisin bread loaf. Picture yourself making this bread. You mix the dough and you knead in a bunch of raisins fairly evenly throughout. Now you put that lump of dough in a warm oven and wait. As the bread bakes, the dough begins to rise, to expand. What happens to the raisins? Every single raisin starts to move away from every other raisin. There is no special raisin at the center that all the others are fleeing from. From the perspective of any one raisin, it would see all its neighbors receding, with the ones farther away moving faster because there's more expanding dough between them. This is a near-perfect model for our homogeneous, isotropic expanding universe, where the galaxies are the raisins and the dough is the fabric of space-time itself. Another classic and perhaps even more direct analogy is the inflating balloon. Take a partially inflated balloon and use a marker to cover its surface with random dots. Now start blowing more air into it. As the balloon expands, what do you see? Every dot moves away from every other dot. The two-dimensional surface of the balloon is representing our three-dimensional space. The key insight here is that the dots aren't moving across the surface of the balloon. They are being carried apart by the stretching of the material they are attached to. This perfectly illustrates that galaxies are not simply flying through a static space. They are co-moving with the expansion of space. If you were to measure the recession speeds, you'd find that a dot twice as far from you as another would be receding at twice the speed, mirroring the Hubble-LeMaitre law. This analogy is powerful because it also visually demonstrates there is no center on the surface of the balloon. The center of the balloon is inside the balloon, in a higher dimension that isn't part of the expanding surface. This hints at the complex geometry of our universe, which may also be curved in ways we can't directly see from within it. We can also think in terms of a simpler, one-dimensional analogy, a stretching rubber band. Imagine you take a rubber band and mark it with evenly spaced ink dots. Now grab both ends and pull, stretching it to twice its original length. The dots are now all farther apart. The space between each pair of dots has grown. This is the essence of metric expansion applied to a line. To add the element of time, imagine the rubber band is being stretched very slowly and smoothly. A photon of light represented by a tiny ant could start walking from one dot to the next. As the ant walks, the rubber band is stretching beneath its feet, making its journey longer and more arduous than it initially appeared. This gives an intuitive feel for how light gets stretched and loses energy during its long cosmic voyages. While these analogies are incredibly useful, it's crucial to understand their limitations to avoid forming the wrong intuition. The balloon, for instance, has a clear center inside the balloon and a definite edge. Its surface is finite. Our universe, as far as we can tell, does not have a center that we can point to, and we have no evidence that it has an edge or a boundary. The raisin bread also expands into the space of your oven, but the universe isn't expanding into anything. It is all there is. There is no outside into which it grows. It is simply getting bigger. The stretching rubber sheet analogy, often used for gravity, can be misapplied here. Expansion isn't a stretch caused by a weight in the center. It's a uniform stretch happening everywhere at once. The goal of these thought tools isn't to provide a perfect replica, but to build a conceptual bridge. They allow your mind to latch onto a familiar process: bread rising, a balloon inflating, and use that framework to comprehend the much stranger reality of the cosmos. The best part is that you can come up with your own. Maybe you think of it like a video game map that's being generated and stretched at its edges as you move. Or perhaps it's like being on a vast, expanding mesh grid where the squares are constantly getting larger. What analogy makes sense to you? The act of creating your own metaphor is one of the best ways to truly internalize and own a complex idea, transforming a distant astronomical fact into a personal understanding of how the universe works. Now, to truly grasp the engine behind this cosmic stretching, we need to introduce a single, powerful number that acts as the master control for the entire universe. This is the scale factor, represented by the symbol A of T, where T stands for time. Think of the scale factor as the universe's volume dial. When the dial is turned low, the universe is small and compressed. As the dial is turned up, the universe expands, and all distances within it are multiplied by this ever-increasing number. Imagine two galaxies at rest within the expanding fabric of space. We can assign them fixed coordinates, like points on an infinite, stretching grid. The actual physical distance between them isn't constant. It's equal to their coordinate separation multiplied by this scale factor, A of T. So if the scale factor doubles, the distance between them doubles. They aren't engines roaring away from each other. They are like two friends standing still on opposite ends of a stretching rubber band, carried apart by the growth of the material between them. This elegant idea transforms expansion from a vague concept into a precise, mathematical description. The Hubble parameter that gives us the current expansion rate is essentially the growth rate of this scale factor. It's how fast that universal volume dial is being turned right now. This scale factor isn't just a standalone idea. It's the star of the show in perhaps the most important equations in all of cosmology, the Friedmann equations. Named after the Russian physicist Alexander Friedmann, these equations are derived from Einstein's theory of general relativity, and they act as the universe's instruction manual. They tell us exactly how the scale factor must evolve over time based on what's inside the universe. The equations take the total energy density of the cosmos, the combined contribution of ordinary matter, dark matter, radiation, and dark energy, and they output the destiny of the scale factor. Will it expand forever? Will it eventually contract? The Friedmann equations hold the answer, making them the fundamental blueprint for cosmic evolution. The behavior of T over the universe's 13.8 billion year history is a fascinating story with distinct chapters. In the very early universe, dominated by radiation and incredibly high densities, the scale factor increased at a ferocious rate during a period called inflation. After that, for billions of years, the universe was dominated by matter. The mutual gravitational attraction of all that matter acted like a cosmic brake, causing the scale factor to increase, but at an ever-decelerating pace. It was as if the volume dial was still being turned up, but with a weakening hand. Then, around 5 billion years ago, a new chapter began. The density of matter dropped enough due to the expansion and the repulsive force of dark energy, which does not dilute with expansion, became dominant. This caused a profound shift. The expansion began to accelerate. The scale factor started increasing at a faster and faster rate, as if an invisible, relentless force had taken over and begun cranking the dial with growing intensity. We can actually measure the history of this scale factor by looking at the light from the distant past. This is where the direct link to redshift comes in. The cosmological redshift of a galaxy, that Z-value astronomers measure, isn't just a random number. it is directly defined by the scale factor. Specifically, the redshift tells us how much the universe has expanded since the light was emitted. If we observe a galaxy with a redshift of 1, it means the scale factor of the universe today, a now, is twice what it was a then when the light left that galaxy. A redshift of 2 means the universe is 3 times larger now than it was then. The light's wavelength has been stretched by exactly the same factor that the universe itself has expanded. This makes redshift a direct time machine. It's a readout of the universal scale factor at the moment of emission, allowing us to piece together the expansion history. Some of our most powerful evidence for this story comes from the cosmic microwave background radiation. This ancient light, emitted when the universe was a mere 380,000 years old, has a staggeringly high redshift of about 1,100. This tells us that the scale factor of the universe today is about 1,100 times larger than it was when that light was released. By meticulously mapping the tiny temperature fluctuations in this background glow, cosmologists can determine the precise composition of the universe, the amounts of matter, dark matter, and dark energy that must have been present to produce the scale factor's evolution that we observe. It's a breathtaking feedback loop. We use the light of the ancient universe to measure the ingredients, and then we use those ingredients in the Friedmann equations to perfectly predict the expansion history that led to the universe we see today. This mathematical framework isn't just abstract speculation. It's a tested and verified narrative of our cosmos with the humble scale factor of T as its silent, unwavering protagonist. But to truly understand the fate of this cosmic expansion, we must meet the 2 invisible giants that rule our universe, locked in an epic tug of war that has shaped its entire history. On one side, we have dark matter, the mysterious, invisible scaffolding that pulls the universe together through gravity. On the other, dark energy, the even more enigmatic force that pushes the universe apart. They are the yin and yang of cosmology, utterly different in nature, yet together making up over 95% of everything that exists, while the stars, planets, and everything we see and know are just the faint, visible froth on this dark, deep ocean. Let's start with dark matter, the cosmic glue. We can't see it because it doesn't emit, absorb, or reflect any light. It simply doesn't interact with electromagnetic radiation at all. But we know it's there because of its powerful gravitational pull. The first major clue came from the way galaxies spin. Our Milky Way, like all spiral galaxies, rotates like a giant pinwheel. According to the laws of gravity, stars on the outer edges of a galaxy should orbit much more slowly than those near the center, just as Pluto orbits the Sun far more slowly than Mercury does. But when astronomers like Vera Rubin measured the orbital speeds of stars in distant galaxies, they found something shocking. Stars on the outskirts were orbiting just as fast as those near the center. The entire galaxy was rotating as if it were a single, solid disk. The only explanation was that each galaxy is enveloped in a massive, invisible sphere of matter, a dark matter halo, whose immense gravitational pull is whipping those outer stars around at high speed. Without this dark matter anchor, these galaxies would have simply flown apart billions of years ago. The evidence doesn't stop there. When we look at the large-scale structure of the universe, the vast cosmic web of galaxies and galaxy clusters strung along invisible filaments separated by enormous voids, we see the handiwork of dark matter. Its gravitational pull acted as a seed, gathering ordinary matter into the dense knots where galaxies would eventually form. We can even see its gravitational influence through a phenomenon called gravitational lensing, where the light from distant galaxies is bent and distorted as it passes through the powerful gravitational fields of unseen clumps of dark matter. It is the great cosmic architect, the unseen structure that gives the universe its form. Now enter the opponent, dark energy. If dark matter is the ultimate attractor, dark energy is the ultimate repulsor. It isn't clumpy or granular like matter. It appears to be perfectly smooth and uniform, a property of space itself, and its effect is the exact opposite of dark matter's gravity. Instead of pulling things together, it causes space to expand. Think of it as a kind of anti-gravity, a steady pressure infused into the vacuum of empty space that pushes galaxies apart. Its discovery, as we discussed, came from observing distant supernovae and finding that the universe's expansion is not slowing down due to gravity's pull, but is instead accelerating. This sets the stage for the greatest tug of war in all of nature. For most of the universe's history, dark matter was the undisputed champion. In the dense, early universe, gravity was the dominant force. The expansion was slowing down as the collective gravitational pull of all the matter in the cosmos acted as a brake on the initial momentum of the Big Bang. Dark matter was diligently working to pull everything back together, to build structure and create the cosmic web. Imagine a ball thrown upward from Earth. Gravity steadily slows its ascent. But as the universe expanded, the density of matter, both dark and normal, began to drop. The number of particles in any given volume of space was decreasing. Dark energy, however, is thought to be a property of space itself. As the universe grew and more space came into existence, the amount of dark energy actually increased. There's more repulsive force in a larger volume of space, so around 5 billion years ago, a cosmic tipping point was reached. The universe had expanded enough that the density of matter fell below the density of dark energy. The balance of power shifted. The repulsive force of dark energy overcame the attractive force of gravity, and the expansion of the universe began to accelerate. It was as if that ball thrown upward suddenly encountered a mysterious force that started pushing it faster and faster into the sky, against all expectations. This ongoing battle between these two dark titans is what will determine the ultimate fate of everything. Right now, dark energy has the upper hand, and the acceleration is relentless. But the nature of dark energy is still the biggest mystery in physics. Is it a constant force, as Einstein's cosmological constant suggests, or is it a dynamic field that could change over time, perhaps even switching from repulsive to attractive one day? The answer to this question will tell us whether our universe will continue expanding forever into a cold, dark, lonely future, or if the tug of war might yet have another surprising twist in store. These two invisible forces, one building and the other dissolving, have been wrestling for control since the beginning of time, and their struggle is written in the very fabric of our expanding cosmos. But to truly appreciate the grand, steady expansion we witness today, we must rewind the cosmic clock all the way back to its very first moments, to an event of such unimaginable violence and energy that it makes every supernova look like a flickering candle. This is the Big Bang, the origin of everything space, time, matter, and energy. And for decades, this brilliant theory had a few puzzling problems that seemed to defy explanation. The universe is incredibly uniform. In every direction we look, the temperature of the cosmic microwave background is the same to within 1 part in 100,000. How did regions of the universe that are now billions of light years apart, and thus could never have been in contact with each other, manage to coordinate their temperature so perfectly? It's as if you walked into a vast concert hall with 1 million people, and without any signal, everyone began humming the same exact note in perfect unison. It simply doesn't make sense with a standard, steadily expanding Big Bang. Then, in the late 1970s, a young physicist named Alan Guth, working at the Stanford Linear Accelerator Center, had a series of insights that would revolutionize our understanding of the beginning. He proposed a breathtaking addendum to the Big Bang theory, a period of hyper-fast, exponential expansion called cosmic inflation. Picture the universe in the first fraction of a second of its existence, perhaps at 10 to the power of negative 36 seconds old. At that moment, a peculiar type of energy field, something like a supercharged version of the dark energy we see today, became trapped in a weird quantum state called a false vacuum. This state had a magical and terrifying property. It generated a tremendous repulsive gravitational force. What happened next is almost beyond description. This repulsive gravity caused the fabric of spacetime itself to expand at a rate that is utterly incomprehensible. In the tiniest sliver of time, perhaps from that moment until 10 to the power of negative 32 seconds later, the universe doubled in size and then doubled again and again and again. In perhaps 100 doublings, a region of space smaller than a single subatomic proton was stretched to a size larger than our entire observable universe today. This wasn't just fast expansion, it was exponential, faster than light inflation that took a quantum speck and blew it up into a macroscopic cosmos in less than the blink of an eye. This incredible burst of growth solves those cosmic puzzles with elegant simplicity. The reason the universe is so uniform is that everything we see today was once crammed into that tiny, subatomic region where everything was in thermal contact, able to easily smooth out any irregularities. Then inflation took that perfectly balanced, ultra-dense marble and stretched it to a size far beyond our horizon, locking in that uniformity across a volume of space so vast we are still only seeing a small part of it. Furthermore, inflation explains why the universe is so remarkably flat without any large-scale curvature. Imagine taking a tiny, crumpled piece of paper and then inflating it to the size of the Earth. The surface of that paper would appear perfectly flat and smooth to an ant walking on it, no matter how wrinkled it was to start. Inflation did the same thing to the geometry of our universe, ironing out any initial curvature into the flat expanse we measure today. But perhaps the most beautiful consequence of inflation is how it created the seeds for all future structure. According to quantum mechanics, empty space is not truly empty. It is a seething foam of quantum fluctuations, with particles and energy constantly flickering in and out of existence. In that primordial, microscopic universe, these tiny quantum ripples were everywhere. Then inflation hit. As space-time expanded at a fantastic rate, it stretched these microscopic quantum fluctuations along with it, magnifying them from the quantum realm to cosmic proportions. A tiny density fluctuation that was smaller than an atom one moment became a vast, region-spanning variation in energy the next. These stretched fluctuations became the slight over-densities and under-densities in the early plasma. After inflation ended and the universe settled into the more sedate expansion of the standard Big Bang, gravity got to work on these seeds. The slightly denser regions had a bit more gravitational pull, slowly attracting more and more matter over hundreds of millions of years, eventually collapsing into the first stars, galaxies, and the immense cosmic web we see today. Every galaxy, every star, every planet, and every one of us originated from a minuscule quantum fluctuation that was amplified to cosmic size during that violent, inflationary birth. This incredible theory, first fully articulated by Alan Guth and then greatly expanded upon by physicists like Andrei Linde with his concept of chaotic eternal inflation, is not just a beautiful story. It makes specific, testable predictions. The most powerful evidence comes from the detailed map of the cosmic microwave background. The theory of inflation predicts that the primordial quantum seeds should have left a specific fingerprint on this ancient light, a nearly scale invariant spectrum of fluctuations. This is a fancy way of saying that the tiny temperature variations we see in the CMB should be of roughly the same magnitude, whether we look at a large patch of sky or a small one. And when satellites like COBE, WMAP, and most recently Planck mapped the CMB with exquisite precision, that is exactly what they found. The data matches the predictions of inflation with stunning accuracy. The theory also predicts the existence of a background sea of gravitational waves, ripples in spacetime, from this violent inflationary period. While these have not yet been directly detected, their indirect signature is actively being hunted in the polarization patterns of the CMB, and their discovery would be the ultimate smoking gun for this explosive genesis. So the expansion we see today, the gentle stretching of space carrying galaxies apart, is merely the long, slow aftermath of this initial, breathtakingly violent event. The Big Bang wasn't just an explosion in space. It was the explosive emergence of space itself, kicked into overdrive by a period of inflationary expansion that set the stage for everything to come. It gave us a universe that is large, flat, uniform, and most importantly, filled with the seeds of complexity that would eventually grow into stars, planets, and us. It shows us that the cosmos is not only expanding, but that it had a beginning of such incredible power and grandeur that it forever redefines our sense of place and wonder. But if we rewind that idea of inflation back to its ultimate conclusion, we are faced with a possibility so vast it redefines the very meaning of reality. What if our entire universe, with its hundreds of billions of galaxies stretching across nearly 100 billion light-years, is just a single bubble in a cosmic ocean of universes? This is the breathtaking realm of multiverse theories, and it emerges directly from the same physics of exponential expansion that gave us our own Big Bang. The concept is known as eternal inflation, and it suggests that the process that created our universe isn't a one-time event that started and stopped. It might be a perpetual, endless engine of creation, constantly giving birth to new universes in a multiverse that has no beginning and no end. Imagine a vast, infinite ocean. This ocean isn't made of water, but of a peculiar, high-energy state of space called the inflaton field. This field is everywhere, and it's constantly seething with quantum fluctuations, tiny, random jumps in energy. Most of the time, these fluctuations are small and quickly settle down, but occasionally, through random chance, a particularly large quantum fluctuation occurs in a local patch of this field. In that patch, the energy drops suddenly and dramatically, like a bubble instantly forming in a pot of water just before it boils. When that energy drops, the false vacuum energy that was driving the repulsive gravity is released, and that local patch undergoes an incredible, hyper-fast inflation, just like the one we think started our cosmos. It expands at a fantastic rate, quickly smoothing out and cooling down, becoming a separate, isolated pocket universe with its own distinct properties and laws of physics. It pinches off from the surrounding high-energy ocean, a self-contained bubble floating in a much larger meta-universe. And here's the key: while that one bubble is forming and inflating, the rest of the ocean, the vast background inflaton field, is itself expanding. In fact, it's expanding even faster than the bubbles are forming. So the overall process never stops. For every one bubble universe that forms, the background space expands so much that it creates room for 1,000,000 more bubbles to form. It becomes a self-sustaining, eternal process, a frothing, bubbling, endlessly generative ocean of reality, where new universes are constantly nucleating, inflating, and drifting apart forever. Our universe would be just one bubble among an infinite number, one page in an infinite book of cosmic possibilities. This idea, championed and refined by theorists like Alexander Vilenkin and Andrei Lind, takes the stunning violence of inflation and extends it into a truly eternal and unimaginably vast landscape. This leads to a question that stretches the mind to its absolute limit. If other universes exist in this eternal inflation foam, could the very nature of expansion be different there? In our universe, we have a specific Hubble constant, a specific strength to dark energy, and specific fundamental constants that dictate how space stretches. But what if, in another bubble, the quantum fluctuation that started it was slightly different? What if the laws of physics there allow for a different cosmological constant, or perhaps no dark energy at all? In one universe, expansion might be so ferociously fast that matter never has a chance to clump into galaxies, resulting in a forever empty, thin haze of particles. In another, expansion might be so weak that gravity quickly wins, causing a big crunch only moments after the bubble forms. There could be universes where expansion is cyclical, with periods of growth and contraction, or universes where the stretching of space is not uniform, but twisted and warped in strange dimensions we can't even conceive. This isn't just wild speculation. It potentially solves one of the deepest mysteries in physics: why our universe seems so finely tuned for life. The strength of dark energy in our cosmos, for instance, is inexplicably small. If it were much larger, the universe would have expanded so rapidly that no stars or galaxies could ever have formed. The fact that we exist in a universe with just the right amount of expansion to allow for complexity might not be a miraculous coincidence, but a simple selection effect. In an infinite multiverse where every possible set of physical laws is realized in some bubble, we naturally find ourselves in one of the rare universes where the expansion rate and constants are just right for life to emerge. We are living in a cosmic neighborhood that is habitable, while most of the multiverse may be a barren, hostile wasteland of failed physics. This idea, known as the anthropic principle, gives a fascinating context to our existence, not as the center of creation, but as a fortunate outcome in a vast and mostly inhospitable meta-reality. But how do we actually know all this? How do we go from abstract theory to precise numbers like the Hubble constant? The answer lies in a breathtaking combination of cutting-edge technology and ingenious methods, a global effort that turns the cosmos itself into a laboratory for measuring its own expansion. This isn't a single detective solving a case. It's a worldwide team of astronomers and engineers using every tool at their disposal to piece together the universe's expanding story. The foundational tools are, of course, our great observatories. For decades, the Hubble Space Telescope has been an indispensable workhorse in this effort. Orbiting above the distorting effects of Earth's atmosphere, Hubble's sharp vision has allowed it to peer deeper into space and further back in time than any telescope before it, precisely measuring the distances and redshifts of countless galaxies. Now the James Webb Space Telescope has joined the hunt, its infrared eyes perfectly suited to see the most ancient, redshifted light from the universe's infancy. These telescopes are the time machines that collect the raw data, but they need a way to interpret it. That's where the concept of a standard candle comes in, an object in space whose intrinsic brightness we know with great confidence. If you know how bright something truly is, and you measure how dim it appears from Earth, you can calculate its distance with remarkable accuracy. It's like knowing the wattage of a light bulb. By seeing how faint it looks, you can tell exactly how far away it is. The most famous and crucial standard candle in modern cosmology is the Type 1 a supernova. These are spectacular stellar explosions that occur when a white dwarf star in a binary system steals just enough matter from its companion to tip it over a critical mass threshold, triggering a thermonuclear detonation. The beautiful thing about these explosions is that they all reach nearly the same peak brightness because the critical mass that triggers them is always the same. This makes them fantastic cosmic mile markers. Teams like the Supernova Cosmology project and the High-Z Supernova Search team used these brilliant beacons to make the landmark discovery of the accelerating universe. By comparing the observed dimness of extremely distant Type 1a supernova to their known intrinsic brightness, they could see they were farther away than expected in a universe that was merely coasting. Their light had been stretched not only by the expansion that occurred while it traveled, but by an additional, accelerating stretch of space itself. This work continues today with even greater precision. The SH0ES project, led by Nobel laureate Adam Rees, has been meticulously observing these supernovae along with Cepheid variable stars, another type of standard candle used to calibrate distances, to pin down the Hubble constant with an uncertainty of less than 2%. Their latest measurements suggest an expansion rate of about 73 kilometers per second per megaparsec, but the cosmic distance ladder has more than one rung. Another powerful technique relies on the frozen echoes of the early universe, patterns known as Baryon acoustic oscillations. Imagine the universe in its first few 100,000 years, a hot, dense plasma of particles and light. In this primordial soup, gravity was trying to pull matter together, but the intense pressure of radiation was pushing it apart. This created spherical sound waves that rippled outward through the plasma. Then, the universe cooled just enough for atoms to form, allowing light to travel freely in what we call recombination. At that moment, those sound waves were frozen in place, imprinting a specific scale onto the distribution of matter, a preferred distance between clumps of galaxies. This scale, about 500 million light-years across, acts as a permanent standard ruler etched into the fabric of the cosmos. By conducting enormous galaxy redshift surveys, like the Sloan Digital Sky Survey, astronomers can measure this characteristic scale at different epochs in the universe's history. They can see how this standard ruler appears to us at different redshifts, and because they know its true size, they can calculate how much the universe has expanded in the time it took the light to reach us. This provides an independent and incredibly precise measurement of the Hubble constant and the properties of dark energy. This is where the plot thickens and one of the most exciting debates in modern cosmology emerges, the Hubble tension. The measurements from the local universe, using the distance ladder of Cepheids and Type 1a supernova, consistently give a higher value for the Hubble constant around 73. Meanwhile, measurements from the early universe, using the pristine data from the Planck satellite's map of the cosmic microwave background, combined with the assumption of a standard cosmological model, predict a lower value around 67. These two methods, both exquisitely precise, disagree by a small but statistically significant amount. This isn't an error, it's a tantalizing discrepancy. It could mean there is a subtle, unaccounted for systematic error in one of the methods, or more thrillingly, it could be a crack in our standard model of cosmology, a hint of new physics. Perhaps dark energy is not a constant but evolves over time. Maybe there is an unknown type of neutrino or some other exotic particle that influenced the early universe's expansion rate. The Hubble tension is not a crisis but an opportunity, a puzzle that is driving the development of even more powerful telescopes and sophisticated techniques, a reminder that science is a dynamic, living process of inquiry and discovery, constantly refining our picture of reality. So where is all this heading? The relentless expansion of space, now accelerating under the influence of dark energy, isn't just a curious feature of our universe, it's the director of its final act. The ultimate fate of everything, every galaxy, every star, every atom, and every moment of consciousness hinges on the precise nature of this mysterious force. Based on our current understanding, cosmologists have sketched out two profoundly different, yet equally dramatic, endings for the cosmos. One is a long, slow, cold fade into oblivion. The other is a violent, catastrophic shredding of reality itself. The first and long-standing favorite scenario is known as the heat death, or sometimes the Big Freeze. This is the future that emerges if dark energy behaves like a true cosmological constant, maintaining its current repulsive strength indefinitely. In this timeline, the acceleration continues at its present steady pace. Billions of years from now, the last stars will use up their fuel and flicker out. Galaxies will continue to drift apart, their light stretching into wavelengths so long and feeble they become undetectable. The universe will become a progressively darker and colder place. Eventually, even the supermassive black holes that once anchored galaxies will, over almost unimaginable timescales, slowly evaporate away through a process called Hawking radiation. What remains is a universe that has reached a state of maximum entropy, a perfect, uniform, and frigid equilibrium. It is a cosmos where the temperature everywhere approaches absolute zero, where no energy gradients exist to perform any work, and where no new events of any kind can ever occur. It is not an explosion or an implosion, but the ultimate stillness, a silent, dark, and eternal exhaustion where time itself becomes meaningless, as there is no change left to mark its passage. But there is a second, far more violent possibility on the table, one that emerged as we began to ponder the potential variations in dark energy's character. This is the scenario known as the Big Rip. It unfolds if dark energy is not a constant, but something more sinister and potent. Specifically, if its repulsive force actually increases over time, a hypothetical form dubbed phantom energy. In this model, the equation of state of dark energy, denoted by the letter W, which is currently very close to -1, would be less than -1. This small mathematical difference has apocalyptic consequences. It would mean that the acceleration isn't just constant, it's exponential and self-reinforcing. The expansion rate wouldn't just increase, it would skyrocket toward infinity in a finite amount of time. The sequence of events in a Big Rip is not a slow fade, but a rapid, terrifying unraveling. First, the acceleration would overcome the gravitational bonds holding galaxy clusters together. They would be torn apart, their member galaxies flung into the ever-widening void. Next, the force would rip into individual galaxies themselves. The Milky Way, Andromeda, and all others would be shredded, their stars scattered into the nothingness. Then it would come for solar systems. The space between a star and its planets would expand so violently that planets would be ripped from their orbits. But the horror wouldn't stop there. The phantom energy would then attack the very fabric of matter itself. The expansion force would overcome the electromagnetic bonds holding molecules together, tearing apart asteroids, planets, and any remaining objects. In the final moments, in the last fraction of a second before the end, the stretching of space would become so ferocious that it would overcome the strong nuclear forces holding atomic nuclei together. Every atom in the universe would be explosively disassembled into its fundamental particles, which would then be instantly carried apart by the inflating space, forever isolated and unable to ever interact again. The universe would end not with a whimper, but with a scream, a final, instantaneous moment of catastrophic disintegration that leaves behind nothing but an empty, featureless void, expanding at an infinite rate. The choice between these two fates rests entirely on a single, elusive number, the equation of state parameter W for dark energy. If W is exactly -1, we get the heat death. If W is less than -1, we get the Big Rip. Our current best measurements from missions like Planck place W very close to -1, slightly favoring the long, cold freeze. But the uncertainties in our measurements are still large enough that we cannot yet completely rule out the phantom energy possibility. Determining this value with absolute precision is one of the primary goals of next-generation observatories like the Nancy Grace Roman Space Telescope and the Euclid mission. They will map the expansion history of the universe with unprecedented detail, hoping to finally pin down the true nature of dark energy and tell us which apocalyptic finale is written into the fundamental laws of physics. Pondering these distant futures forces a profound shift in perspective. On a human timescale, these events are so far in the future that they hold no practical threat. But as a thought experiment, they ask us to consider the ultimate context of our existence. Does the inevitability of a cold, dark end diminish the meaning we find in our lives today? Or does it, in a strange way, make every moment of warmth, connection, and discovery infinitely more precious? If the universe is ultimately transient, destined to either freeze or be torn apart, then the brief flicker of consciousness we experience is a rare and beautiful spark of light in an immense and mostly empty darkness. It suggests that meaning isn't something to be found in the cosmos's ultimate fate, but something we create right here, right now, in the temporary structures we build against the silent, expanding night. The story of the universe may have a final page, but we are the authors of the story we tell within it. This relentless cosmic expansion, this silent tide pulling the galaxies apart, forces us to confront questions that go far beyond physics and mathematics. It pushes us into the realm of philosophy, asking what any of this means for us tiny, thinking beings on a small rock in an ever-growing sea of darkness. If the universe is fundamentally transient, if all structure is ultimately destined to dissolve into a cold, diffuse haze or be violently torn apart, does that rob our lives of meaning? Or could this very impermanence be the very thing that makes our existence so precious and unique? One of the most beautiful perspectives comes from the late astronomer Carl Sagan. He didn't see the vastness and transience of the cosmos as something to fear, but as a source of profound wonder and connection. His famous reflection that we are a way for the cosmos to know itself reframes our entire place in the universe. We are not just passive bystanders on a random planet. We are the universe become self-aware. The same cosmic processes that forged hydrogen and helium in the Big Bang, that cooked heavier elements in the hearts of exploding stars, eventually arranged those atoms into planets, oceans, and living, breathing, thinking creatures. In us, the universe has developed eyes to see its own grandeur, minds to comprehend its own laws, and hearts to feel awe at its own story. The expansion isn't a meaningless drift into nothingness. It's the stage upon which this incredible act of self-discovery plays out. The fact that it is temporary doesn't diminish the miracle. It makes the fact that it happened at all even more astonishing. This stands in contrast to a more existentialist view, which might find a deep, unsettling isolation in this cosmic narrative. If distant galaxies are forever receding beyond our event horizon, if we are ultimately alone in a vast and growing void, then one could interpret this as the ultimate form of abandonment. The universe seems indifferent, a cold, mechanical process operating on a scale that utterly dwarfs human concerns. The French philosopher Jean-Paul Sartre spoke of a universe devoid of inherent meaning, where we are condemned to be free to create our own purpose. The accelerating expansion could be seen as the ultimate expression of that existential freedom, a universe that provides no answers, no comfort, and no ultimate destination, leaving us completely responsible for finding or building meaning right here, right now, in the face of the immense and silent dark. But perhaps these two views aren't mutually exclusive. Maybe they are two sides of the same cosmic coin. Sagan's awe and the existentialist's responsibility can merge into a powerful third perspective. The universe's impermanence is what makes every moment of connection, every spark of creativity, and every act of love so vitally important. In a universe that will eventually forget everything, the things we do matter more, not less, because they are rare and fleeting. A sunset is beautiful precisely because it ends. A song is moving because its notes fade into silence. Our lives, our cultures, our art, and our scientific discoveries are like brilliant fireworks against a dark sky. Their beauty is inextricably linked to their temporariness. The expanding cosmos provides the ultimate dark canvas against which our brief, bright flame of consciousness burns all the more fiercely and significantly. This leads to a very personal question for all of us. How does knowing this change how you choose to live your life? Does it make you want to retreat from a universe that seems to be drifting away, or does it inspire you to connect more deeply with the people and the world right in front of you? It can be a call to cherish our local gravitational bonds, our families, our communities, our planet, all the more, because they are the real, tangible things that hold us together against the vast, dispersing background. The cosmos may be expanding, but we can choose to contract, to draw closer, to build things of meaning and beauty that, while they may not last forever, will shine brilliantly in the time we have. We are the universe's way of experiencing joy, curiosity, and wonder, and that is a role we should embrace with both humility and passion. Science fiction has long been a playground for the mind, a genre where we can take the most profound ideas from cosmology and run with them, exploring their human implications in ways that raw equations never could. And the concept of the expanding universe, with its themes of inevitable distance and deep time, has provided an incredibly rich backdrop for some of the most memorable stories ever told. These narratives often grapple with the profound isolation that expansion implies, painting pictures of civilizations adrift on an ever-widening ocean of space. Think of the classic trope of the generation ship, a vessel sent out from a dying Earth, its passengers destined to live and die in the void, their descendants arriving at a new world so far in the future that the home they left behind is itself just a forgotten legend. This is a direct narrative embodiment of the Hubble flow, the idea that journeys between galaxies become not just difficult, but fundamentally impossible over cosmic timescales, separating branches of humanity forever. Perhaps no story has wrestled with the ultimate fate of the cosmos more poetically than Isaac Asimov's The Last Question. Written in 1956, it follows the journey of a supercomputer called the multivac across trillions of years, through the era of stellar death and into the heat death of the universe itself. Each time, humanity in its various forms asks the computer the same question: how can the net entropy of the universe be massively decreased? Or in simpler terms, how can the heat death be reversed? And each time the computer responds with the same answer, insufficient data for meaningful answer. The story is a stunning exploration of deep time and the eventual dissolution of all energy gradients, a direct narrative take on the second law of thermodynamics and its implications in an expanding, accelerating universe. Yet in its famous mind-bending twist, Asimov offers a spark of hope, a suggestion that even at the end of all things, a new beginning might be possible, blending scientific awe with an almost spiritual sense of wonder. Where these stories often take creative license, however, is in their mechanical portrayal of expansion itself. Much of science fiction, especially in visual media like film and television, inadvertently reinforces a common misconception. We often see galaxies depicted as objects flying through a static space, like ships sailing on a motionless sea. The iconic opening crawl of Star Wars, for instance, shows stars streaking past as if the spacecraft is moving through them. This intuitively makes sense to our brains, which are wired to understand motion within a container. But as we've learned, the reality of cosmic expansion is far stranger. It's not that galaxies are rocketing away from each other through space. It's that the very space between them is itself stretching, creating more distance without any traditional motion involved. This is a much harder concept to visualize, which is why it's so often simplified or misrepresented. You almost never see a science fiction show depict two characters standing still on a planet while the space between them and their home world silently elongates, because that subtle, geometric effect lacks the dramatic punch of a roaring engine or a streaking starfield. But this isn't really a failure of storytelling. It's a challenge of translation. The job of science fiction is not to provide perfect pedagogical models, but to capture the emotional and philosophical weight of scientific ideas. A story like Arthur C. Clarke's The Star isn't concerned with the precise metric expansion of space. It's concerned with the crushing existential dread a spacefaring priest feels when he discovers that the stellar explosion that served as the biblical Star of Bethlehem also obliterated a beautiful, peaceful alien civilization. The science is the setup for a human dilemma. Similarly, the endless expansion of the universe provides a powerful backdrop for stories about loneliness, the search for connection, and the fragility of memory across astronomical distances. These narratives may take liberties with the precise mechanics, but they succeed magnificently in conveying the feel of a vast, lonely, and ever-growing cosmos, making these abstract ideas tangible and emotionally resonant for millions of people. This cultural impact is arguably as important as the scientific discovery itself. For every person who will ever read a paper on the Friedmann equations, there are thousands who will encounter these concepts through the lens of a beloved novel, film, or television show. The reboot of Battlestar Galactica is steeped in a sense of existential flight through an immense and empty space. The video game franchise Halo features giant, ring-world habitats built as arcs against an impending cosmic dissolution. These stories plant a seed of curiosity in the public consciousness. They make the idea of an expanding universe, dark energy, and heat death part of our shared cultural vocabulary, inspiring countless young minds to look up at the night sky and wonder not just what's out there, but what it all means for the long-term story of life and intelligence. They bridge the gap between the observatory and the living room, proving that the most awe-inspiring discoveries of science are not just for academics in white coats, but are the rightful inheritance of everyone, fertile ground for imagination, speculation, and the timeless human need to tell stories about our place in the grand scheme of things. Now, let's clear the air and tackle some of the most persistent myths that swirl around the idea of cosmic expansion. It's easy for misunderstandings to take root when we're dealing with concepts that defy our everyday intuition, so it's crucial to separate the scientific reality from the common fiction. One of the biggest and most understandable misconceptions is the idea that the universe is expanding from a single, central point, like the fragments of a bomb blast flying outward from the origin of the explosion. This leads to a very natural question. If everything is flying away from everything else, where is the center? Where was the Big Bang? The answer is both simple and mind-bending. There is no center. The expansion of the universe doesn't have a center point because it's not an explosion in space. It is the expansion of space itself. This is where our trusty balloon analogy becomes absolutely essential. Remember, we imagine the two-dimensional surface of an inflating balloon as representing our three-dimensional space. The galaxies are dots on that surface. As you blow up the balloon, every single dot moves away from every other dot. Critically, from the perspective of any dot you choose, it will see all the other dots receding from it. There is no dot that is the privileged center of the expansion on that surface. The center of the balloon exists, but it's inside the balloon, in a third dimension that isn't part of the expanding surface. Our universe operates in a similar way. We can talk about the three spatial dimensions we live in expanding, but the center of that expansion would exist in a hypothetical higher dimension that we cannot perceive or point to. As cosmologist Ethan Siegel often explains, the Big Bang didn't happen at a point in space. It happened everywhere at once. Every point in our observable universe was once crunched together in that initial hot, dense state, and every point has been expanding away from every other point ever since. So when we look out and see galaxies receding from us, it's not because we are at the center of some grand cosmic motion. An observer in any other galaxy would see the exact same thing, all the other galaxies, including our Milky Way, appearing to recede from them. Another very common worry, and one that seems perfectly logical on the surface, is the question of whether we ourselves are expanding. If space itself is stretching, will the Earth eventually get bigger? Will the distance between the Sun and Pluto increase because of this? The answer is a resounding no, and the reason is that the expansion of the universe is an incredibly weak force. It is easily overwhelmed by all the other forces that govern our local reality. The Hubble constant tells us the rate of expansion is about 70 kilometers per second per megaparsec. A megaparsec is a colossal distance, roughly 3.26 million light-years. To put that into perspective, the entire span of our Milky Way galaxy is only about 30,000 parsecs. Over a distance as relatively small as the size of our galaxy, the amount of expansion is utterly negligible. The gravitational pull that holds our solar system together, the electromagnetic forces that bind the atoms in your body together, and the nuclear forces that hold atomic nuclei intact are all astronomically stronger than the feeble background tug of cosmic expansion. It's like trying to use a gentle breeze to pull apart a solid steel beam. The forces involved are so mismatched that the breeze has no effect whatsoever. This is why we have structures like galaxies, solar systems, and planets. Their internal gravity is so powerful that they are effectively decoupled from the Hubble flow. They are not expanding, they are stable, gravitationally bound systems. The expansion of the universe only becomes significant and dominant in the vast, empty voids between galaxy clusters, where the gravitational pull is weak enough that the cumulative stretching of space over those millions of light-years can take over. So you can rest easy knowing that the space between your ears is not getting wider, the Earth is not swelling, and the solar system is in no danger of being pulled apart by the background expansion of the cosmos. Local physics wins every time, and it's what allows us to have a stable universe to live in and observe. A third myth worth dispelling is the idea that the expansion is somehow slowing down or that we have a complete understanding of it. While the discovery of acceleration was a monumental shift, the precise nature of the dark energy causing it remains one of the greatest mysteries in all of science. Some people might hear the word constant in cosmological constant and assume the expansion rate has always been the same. We now know that's not true. For the first several billion years of the universe's life, the expansion was actually slowing down due to the gravitational attraction of all the matter. It was only when the universe became large enough that the density of matter dropped and the repulsive effect of dark energy became dominant that the expansion began to accelerate. Even now, the exact value of the Hubble constant is a topic of intense debate and precise measurement, with a lingering tension between values measured in the local universe and those inferred from the early universe. This isn't a sign that the science is wrong. It's a thrilling indicator that there might be new physics waiting to be discovered, perhaps a subtle evolution in dark energy itself or the presence of an unknown particle. So the next time you hear someone say the universe is expanding, remember they're describing a dynamic, evolving process that is still actively being unraveled by scientists around the world, a story that is far more complex and interesting than any simple myth could ever be. All right, now it's your turn. Let's make this personal. Let's move from the grand cosmic scale to the space right here in your room. I want you to try something with me, a little thought experiment. Find a comfortable position, and if you feel comfortable doing so, just close your eyes for a moment. I want you to picture something in your mind. It could be a person you love who lives far away. It could be a favorite place from your childhood, a mountain you've seen in a photograph, or even the moon hanging in the night sky outside your window. Got it? Hold that image clearly in your mind. Now, I want you to imagine the space between you and that distant point, not as empty nothingness, but as a physical thing, a fabric. And I want you to visualize that fabric beginning to stretch, slowly, silently, relentlessly. That distant point isn't moving away from you in the traditional sense. Instead, the very grid of reality that connects you to it is elongating, like a solitary rubber band being pulled at both ends. The distance is growing, not because either of you are walking away, but because the universe itself is inserting more space into the gap. What does that feel like? Does it create a subtle, low hum of unease, a feeling of helplessness, watching something precious drift away on a current you cannot control, a quiet geometric panic? Or does it spark a sense of profound wonder, the awe of literally feeling in your imagination, one of the most fundamental and powerful processes in all of existence, a force that has been operating since the beginning of time? Perhaps it brings a strange sense of detachment, a quiet realization that the stability we perceive is an illusion, a local phenomenon, and that beneath it all is this constant, silent, cosmic drift. This sensation, this quiet stretching of the soul, is deeply connected to ancient ideas of impermanence that many philosophies and meditation practices explore. The concept that nothing is static, that everything is in a state of flux. We usually apply that to our lives, our relationships, our own aging, but this takes it to the ultimate scale. The very stage upon which existence plays out is itself impermanent, slowly evolving and stretching into a different form. Sitting with this feeling, even for a moment, can be a form of meditation. It's not about inducing anxiety, but about grounding yourself in the true, deep nature of reality, finding a sense of perspective that is both humbling and strangely peaceful. We are temporary beings on a temporary world, living our lives within a universe that is itself engaged in a slow, majestic dance of change. I'd love to know what you felt during that. Did you feel that quiet pull, that sense of wonder or distance? Drop a comment below and let me know what your experience was like. Let's get a conversation going about what it feels like, in your own words, to imagine the cosmos expanding right from where you sit. So we arrive at a beautiful and fundamental cosmic duality, a silent tug of war that defines the very structure of everything we see. On one hand, we have the relentless outward push of expansion, stretching the fabric of space itself. On the other, we have the powerful inward pull of gravity, working to gather matter together into galaxies, stars, and planets. The universe we live in is not governed by one of these forces to the exclusion of the other. It is a dynamic battlefield where their relative strength depends entirely on the scale you're looking at. It's this delicate balance that allows for a cosmos filled with both magnificent structure and relentless growth. Think of it like this: here on Earth and within our solar system, gravity is the undisputed master. It holds you firmly to the ground, keeps the moon in its steady orbit around us, and binds all the planets to the sun. This isn't just a mild preference, it's a complete and total domination. The gravitational forces at play in our local neighborhood are so immensely powerful that they utterly overwhelm the faint background hum of cosmic expansion. The space between the Sun and the Earth is indeed expanding, but the amount of new space created over that distance each second is a minuscule fraction of a millimeter, amount that gravity instantly and effortlessly overcomes. The solar system is a stable, gravitationally bound system, effectively isolated from the Hubble flow. It is an island of stability in an expanding sea. This principle scales up. Our Milky Way galaxy is a vast collection of hundreds of billions of stars, all held together by their mutual gravitational attraction. The same is true for the Andromeda galaxy, our nearest large galactic neighbor. In fact, the Milky Way and Andromeda are not being pushed apart by the expansion of the universe at all. Their mutual gravitational pull is so strong that they are actually hurtling toward each other at a breathtaking 110 kilometers per second, destined to merge in a colossal dance in about 4.5 billion years. They, along with about 60 other smaller galaxies, form what is known as the local group. This entire group is a gravitationally bound structure, a family of galaxies that will stay together forever, orbiting a common center of mass, completely unaffected by the expansion happening outside their door. So where does expansion finally win? Where is the line where the silent stretching of space finally overpowers the clenching fist of gravity? Cosmologists have a concept for this boundary, known as the zero-velocity surface. It's the theoretical point around any massive object, like a galaxy cluster, where the expansion rate of the universe exactly equals the escape velocity caused by that object's gravity. Inside this surface, gravity wins, objects are bound together. Outside this surface, expansion wins, and objects will be carried away from each other by the growing space between them. For our local group, this surface lies just beyond its outer fringe. This means that while all the galaxies within our local group are gravitationally tethered to us, any galaxy beyond that invisible bubble is forever lost to the Hubble flow, destined to recede from us into the depths of the expanding universe. This is why the large-scale structure of the cosmos looks the way it does. When we map the universe, we don't see a perfectly smooth, uniform distribution of galaxies. Instead, we find a magnificent cosmic web, long, dense filaments of galaxies winding their way through the universe, connecting at massive nodes where huge galaxy clusters reside, all separated by vast, empty voids that are hundreds of millions of light-years across. Those filaments and clusters are like continents and mountain ranges. They are the gravitationally bound structures, the places where gravity has successfully held its ground against expansion. The voids, on the other hand, are the territories where expansion reigns supreme. They are the deep ocean between the continents, and they are growing larger and emptier with every passing moment. In these regions, the density of matter is so low that gravity's pull is incredibly weak, and the relentless expansion of space has free rein to stretch these voids ever wider. This elegant duality resolves what might seem like a paradox. We don't have to choose between a universe that is expanding and a universe that is full of stable structures. We have both simultaneously. It's all a matter of scale. Gravity wins the battles locally, creating the beautiful, complex structures that allow for planets, life, and us. But expansion wins the war on the largest scales, setting the overall fate of the cosmos and determining the ultimate isolation of those island universes from one another. Our reality is a tapestry woven from these two fundamental threads, the thread of gravity, which pulls and gathers and builds, and the thread of expansion, which stretches and smooths and disperses. Together, they create the rich, structured, and evolving universe we are privileged to call home. But to truly grasp the origin of this magnificent cosmic web, we have to venture into the most counterintuitive and mind-bending realm of physics, the quantum world. It is here, in the chaotic, probabilistic foam of the very small, that we find the ultimate seeds for everything we see in the vast, large-scale universe. And the bridge that connects these two disparate realms, the quantum and the cosmic, is the violent, exponential expansion of inflation. The story of how infinitesimal quantum jitters were stretched into galactic superclusters is perhaps the most elegant and profound in all of cosmology, a perfect demonstration of how expansion didn't just create space, it created the structures within it. Let's start with a fundamental principle of quantum mechanics, the uncertainty principle. It tells us that on the very smallest scales, at the level of particles and fields, nothing is ever perfectly still or perfectly determined. Even in what we would call a perfect vacuum, a state of complete emptiness, there is a constant seething energy. Particles and their antiparticles spontaneously pop into existence for unimaginably brief moments before annihilating each other and vanishing again. These are quantum fluctuations, tiny, random, and unpredictable jumps in energy that are the signature of the quantum world. They are the universe's ultimate fidgets, an irreducible background static woven into the fabric of reality itself. In our everyday lives, these fluctuations are completely invisible, their effects vanishingly small and localized. Now, rewind the clock to the first fraction of a second after the Big Bang, to that era of inflationary expansion we discussed. The entire observable universe was smaller than a single atom, a domain where quantum effects weren't just noticeable, they were everything. At that moment, the universe was filled with the energy field that drives inflation, often called the inflaton field. And like all quantum fields, it was subject to these tiny, random fluctuations. In one minuscule patch, the field's energy might randomly jump a tiny bit higher. In the patch right next to it, it might dip a tiny bit lower. These were not dramatic events. They were the ordinary, ever-present quantum noise of the early cosmos. Then inflation hit. The universe began to expand at an exponential, faster-than-light rate, and this expansion did something miraculous to those tiny quantum ripples. It took them and stretched them. Imagine you have a perfectly smooth rubber sheet, and you sprinkle a few grains of sand onto it. Those grains represent the tiny quantum fluctuations. Now, imagine you grab the edges of that rubber sheet and pull, stretching it to the size of a football field. Those tiny grains of sand are now vast, continent-sized variations in the sheet's texture. The once microscopic imperfections have been magnified to a macroscopic scale. This is precisely what inflation did. The infinitesimal differences in the energy of the inflaton field from one quantum-sized point to the next were stretched across vast reaches of space. A region where the energy was slightly higher became a vast zone of slightly higher density. A region where the energy was slightly lower became a vast underdense zone. When inflation finally ended, its energy decaying into the hot soup of particles that would fuel the Big Bang, it left behind a universe that was no longer perfectly smooth. It was imprinted with a faint, frozen pattern of density variations, a cosmic fingerprint directly transferred from the quantum realm. These over-dense and under-dense regions were the seeds of all future structure. Gravity, that great cosmic architect, got to work immediately. It began to pull matter, both the normal matter and the dark matter, toward those slightly denser regions. Over hundreds of millions of years, this gravitational attraction amplified the differences. The over-dense regions grew denser, pulling in more and more gas, eventually collapsing under their own weight to form the first stars and the proto-galaxies that would merge into the majestic spirals and ellipticals we see today. The under-dense regions, meanwhile, emptied out, becoming the immense dark voids that separate the great filaments of the cosmic web. Every galaxy, every cluster, every supercluster we observe today can trace its lineage back to a random quantum fluctuation in the first moment of time, a microscopic jump in energy that was magnified to cosmic proportions by the incredible power of inflationary expansion. We are not just theorizing about this, we can actually see this primordial fingerprint. The evidence is written in the oldest light in the universe, the cosmic microwave background radiation. When the CMB was released, about 380,000 years after the Big Bang, the universe was still a relatively simple place. Those primordial density variations were imprinted on this light as tiny differences in temperature. Slightly denser regions were slightly hotter, slightly less dense regions were slightly colder. When satellites like COBE, WMAP, and Planck mapped the CMB with exquisite precision, they found it wasn't perfectly uniform. It is anisotropic, filled with a speckled pattern of hot and cold spots. This pattern is the direct snapshot of those stretched quantum fluctuations. The statistics of these spots, their size, distribution, and magnitude, match the predictions of the inflationary quantum fluctuation theory with stunning accuracy. It is the most powerful evidence we have that the largest structures in the universe were indeed born from the smallest possible vibrations of reality. This connection is nothing short of breathtaking. It means that the quantum fuzz that is an irreducible part of empty space is the very same thing that, when stretched by cosmic expansion, gave rise to the grand tapestry of galaxies, including our own Milky Way, our Sun, our Earth, and ultimately, us. We are the children of quantum noise, our existence made possible by the silent, relentless expansion that transformed randomness into the seeds of cosmic complexity. This profound human urge to explain the cosmos, to find a story for our origins, is not new. Long before Edwin Hubble trained his telescope on the faint glow of distant nebulae, our ancestors looked up at the star-studded sky and told their own powerful stories of a universe being born, stretching, and growing. It's a fascinating and humbling exercise to place our modern scientific narrative of cosmic expansion alongside these ancient creation myths, not to disprove them, but to listen for the echoes of a shared human wonder that transcends time and culture. Across the globe, we find a recurring theme. The universe begins not with a static creation, but with a dynamic act of unfurling, a breathing into being of vast, open space. Consider the ancient Hindu texts which describe the universe cyclically expanding and contracting through the exhalation and inhalation of the deity Brahma. Each outward breath, a day of Brahma or a kalpa, is a period of cosmic expansion and manifestation that lasts for billions of years, a timescale that feels almost cosmological in its grandeur. The imagery isn't of a single static event, but of a living, breathing, oscillating reality. Similarly, the concept of the cosmic egg, appears in creation stories from Finland to China, from the Polynesian islands to ancient Greece. In these myths, the totality of existence is contained within a primordial shell. The birth of the universe comes from the cracking open of that egg, its contents spilling out and expanding to fill the void, organizing themselves into the world we know. The Big Bang Theory, with its initial singularity from which all space, time, and matter emerged, shares a powerful symbolic resonance with this idea of a contained, singular origin point that then rapidly unfolds. We see this theme of expansion in the Norse concept of Ginnungagap, the primordial void that existed before creation, a yawning emptiness that held the potential for everything. The Aboriginal Dreamtime stories of Australia speak of the world being sung into existence by ancestral beings who traveled across the landscape, literally naming and in the process creating the features of the world, a metaphorical expansion of reality out of a formless dream state. Even the biblical book of Genesis, often interpreted as a static, 7-day construction project, contains the potent phrase describing how God stretched out the heavens. The original Hebrew verb used, nata, carries the direct connotation of stretching out a tent or a curtain, an active spreading of a fabric across an expanse. The similarity to our modern analogy of the stretching fabric of space-time is, to say the least, striking. The crucial distinction, and where the dialogue between science and myth becomes most interesting, lies not in the imagery but in the mechanism. Ancient myths are ultimately concerned with meaning, purpose, and agency. The expansion of the world is almost always the act of a conscious creator, a god, a spirit, or an ancestral being. It is a purposeful unfolding with intention behind it, often meant to create a habitat for humanity or to fulfill a divine plan. The driving force is will. Modern cosmology, in beautiful contrast, seeks a mechanism devoid of intention, described through the impersonal, elegant language of mathematics and physical law. The expansion we observe is not guided by a conscious entity, but is the inevitable outcome of the initial conditions of the Big Bang and the mysterious properties of dark energy. It is a process, not a performance. One narrative answers the why, while the other seeks to describe the how. This doesn't mean these two worldviews are locked in an eternal battle. Instead, they offer complementary perspectives on the same profound reality. Science gives us the what, the equations, the data, the observable evidence of an expanding cosmos. It provides a testable, reliable framework for understanding the mechanics of the universe. Myth and religion, on the other hand, often grapple with the so what. They provide a cultural, ethical, and spiritual context for our place within this vast, expanding reality. A creation story is rarely just about the origin of stars. It's about the origin of meaning, of moral codes, and of our relationship to the cosmos and to each other. Knowing the Hubble constant doesn't tell us how to live a good life, but a creation myth often does. This allows for a rich and respectful dialogue. A person can fully accept the scientific description of the Big Bang and the metric expansion of space, while also finding deep spiritual resonance in the image of a deity stretching out the heavens. One explains the process, the other explores its significance. They operate in different realms of human understanding, the empirical and the existential. This holistic view acknowledges that human beings are not just thinking machines that need data. We are storytelling creatures that need meaning. Our curiosity about cosmic beginnings is a dual curiosity, seeking both the factual starting point and the narrative that helps us find our place in the ongoing story. By appreciating the poetic truth of the ancient myths alongside the empirical truth of modern science, we don't diminish either. We become more fully human, capable of holding wonder for the equations on a physicist's blackboard and the timeless stories told under a canopy of expanding space. If this journey through the stretching cosmos has ignited a spark of curiosity, you might be wondering where to go from here. How can you dive deeper into these mind-expanding ideas? The wonderful news is that we live in a golden age of accessibility when it comes to cosmology, with a wealth of incredible resources available for anyone with an internet connection or a library card. Let's start with some truly transformative books that can take you much further down the rabbit hole. For a breathtaking overview that connects the dots between quantum mechanics, space-time, and the cosmos, it's hard to beat Brian Greene's The Fabric of the Cosmos. Greene has a rare gift for translating complex concepts into vivid, relatable prose, making you feel like you're right there with him, visualizing the warping of space-time and the mysteries of the multiverse. Another masterpiece is A Brief History of Time by Stephen Hawking, a book that needs no introduction and remains a beautifully clear exploration of black holes, the arrow of time, and the origin of the universe. For a more recent deep dive specifically into the mysteries of dark matter and dark energy, I highly recommend The Cosmic Cocktail by Catherine Fries, which reads like a detective story as she chronicles the hunt for the universe's missing ingredients. Beyond books, the internet opens up entire universities' worth of knowledge. NASA website has a dedicated cosmology section that is an absolute treasure trove. You can find the latest press releases from the James Webb Space Telescope, stunning visualizations of the cosmic microwave background from the Planck mission, and easy-to-understand explainer articles that break down complex discoveries. The European Space Agency's website is another fantastic source, offering a slightly different perspective on international collaborations. For a more structured learning experience, online learning platforms like Coursera and edX offer full university courses on cosmology, often taught by leading professors from institutions like Caltech and the University of Chicago. These courses typically allow you to learn at your own pace, with video lectures, quizzes, and even discussion forums where you can connect with other curious minds from around the world. Sometimes, after a long day, you might not feel like reading a dense textbook or taking a quiz, and that's where documentaries and podcasts truly shine. The documentary series Cosmos is, of course, iconic. The original with Carl Sagan is a timeless classic, while the reboot hosted by Neil deGrasse Tyson is a visual spectacular that brings the latest science to life with state-of-the-art animation. For podcasts, you can't go wrong with Star Talk, where Neil deGrasse Tyson and his guests blend science, comedy, and pop culture to explore the universe's biggest questions. The Infinite Monkey Cage from the BBC, hosted by physicist Brian Cox and comedian Robin Ince, is another brilliant and hilarious look at the world of science, with episodes dedicated to the Big Bang, dark matter, and the nature of time itself. These audio experiences are perfect for a commute, a walk, or just relaxing while your mind voyages across the cosmos. The most important step in moving from a passive viewer to an active learner is to engage with these ideas yourself. Don't just consume the information, interact with it. Keep a small notebook or a digital document where you jot down questions that pop into your head. What don't you understand? What seems contradictory? Those questions are the starting points for your own personal research. Even better, try to explain a concept you just learned to someone else, even if it's just to your pet or your reflection in the mirror. The act of articulating an idea in your own words is one of the most powerful learning tools there is. If you're feeling ambitious, seek out or start a local or online discussion group. There are countless forums and social media communities filled with amateur astronomy enthusiasts and professional scientists who are almost always thrilled to answer thoughtful questions. The journey to understand the universe is a marathon, not a sprint, and every single one of these resources is a stepping stone that will deepen your appreciation for the incredible, expanding reality we are all a part of. And yet, for all we have discovered, for all the equations we've written and the breathtaking maps we've made of the early universe, we must end this journey by coming full circle to a place of profound humility. We have peered into the deepest reaches of space and time, and what we have found more than any single answer is a beautiful, expanding frontier of mystery. The true nature of the dark energy that's accelerating our cosmos, we don't know. The ultimate fate of everything, whether a silent freeze or a violent rip. We cannot say for certain what happened before the inflationary Big Bang, or if that question even has meaning. We are utterly in the dark, and this is not a failing of science. This is its greatest and most thrilling success. There's a common misconception that the goal of science is to collect facts, to fill a ledger with answers and then close the book, but that's not it at all. Science is a process, a living, breathing conversation with the universe. It's a method for asking better and better questions. Each discovery doesn't just provide an answer, it peels back a layer to reveal a new, more fundamental, and often more puzzling question beneath. The great physicist Richard Feynman captured this spirit perfectly when he said, "I think it's much more interesting to live not knowing than to have answers which might be wrong." He spoke of a vibrant, open uncertainty that is far more exciting than any fixed, closed certainty could ever be. This is the heart of the scientific mindset, a joyous embrace of the unknown, not as a void to be feared, but as a playground for curiosity. This perspective is what separates a sterile list of facts from a truly wondrous exploration. Imagine if we actually knew all the answers, if we had a perfect, complete theory of everything that could predict every outcome and explain every phenomenon. The cosmic story would be over. The sense of wonder would slowly fade, replaced by a kind of mundane, mechanical understanding. The universe would become a solved puzzle, its magic diminished. It is the very presence of these deep mysteries, the unknown nature of 95% of the cosmos, the unresolved Hubble tension, the bizarre fine-tuning of the constants, that keeps the flame of discovery alive. These are not frustrating roadblocks, they are the signposts pointing toward the next revolution in physics, the next Einstein who will look at the same day to everyone else has seen and perceive a completely new truth. This is an invitation to shift how you view knowledge itself. In our daily lives, we often seek quick answers and definitive solutions. We want to know the outcome to resolve the uncertainty. But the cosmos teaches us a different lesson. It asks us to find comfort in the question, to savor the mystery, and to appreciate the journey of exploration as much as the destination. The value is not just in the answers we might one day find, but in the process of looking in the new technologies we invent to see farther, in the brilliant collaborations between minds across the globe, and in the sheer, jaw-dropping awe we feel when we confront just how much there is left to learn. So the next time you look up at the night sky, let yourself feel that awe. Don't just see the pinpricks of light, see the immense questions they represent. See the dark energy silently pushing the galaxies apart. See the dark matter whose invisible grip holds them together. See the light from the edge of time, carrying secrets we are only beginning to decipher. Embrace the beautiful, humbling truth that we are part of a story that is still being written by us and for us. Our greatest achievement is not that we have solved the universe, but that we have chosen to engage with its grandest mysteries, to keep asking, and to find profound joy in the magnificent, never-ending search. So as we bring this cosmic journey to a close, let's gather together the most profound insights from our thought experiment. We've ventured across billions of light years and peered into the deepest nature of reality itself, and what we've found is both humbling and awe-inspiring. The central, mind-bending truth is that cosmic expansion isn't about galaxies rocketing away from each other through a static void. It is the very fabric of space itself that is stretching relentlessly and silently, inserting more of itself between every point in the cosmos. This isn't a motion you could ever feel in your bones or see with your eyes on human scales, because the powerful local forces of gravity and electromagnetism hold everything together, mercifully shielding us from this grand background drift. It's a phenomenon that only reveals its full power on the largest of scales, in the vast, empty voids between galaxy clusters, where the gentle, cumulative tug of stretching space finally overcomes gravity's grasp. And we now know this expansion isn't just happening, it's accelerating, driven by a mysterious repulsive force we call dark energy, a component of the universe that makes up the majority of its energy content yet remains almost completely unknown to us. This discovery upended our entire understanding of cosmic fate, shifting the narrative from an eventual slow coast or a gravitational collapse to an ever-accelerating, ever-cooling future. This relentless expansion fundamentally reshapes our understanding of time itself, stretching the very intervals between events as we look back into the deep past through cosmological time dilation. It dictates the ultimate limits of our observation, setting cosmic horizons beyond which we can never see, and it paints a picture of a future that could either be a long, cold fade into darkness or a violent, catastrophic dissolution of reality itself in a big rip. But beyond the physics and the equations, this journey has been about a deeper, more human kind of understanding. It's about the profound sense of isolation that emerges when you truly internalize that the community of the cosmos is dissolving, with galaxies fading from view like lights on a receding shore. It's about the philosophical weight of existing in a transient universe, and the choice we face to either see that impermanence as a source of despair or as the very thing that makes every moment of connection, every spark of creativity, and every act of wonder infinitely more precious. We've seen how this concept has captivated not just scientists but storytellers and philosophers, all grappling with what it means to be a conscious being on a small planet in an ever-growing sea of spacetime. None of this profound understanding would be possible without the power of imagination. The equations of general relativity and the data from our telescopes give us the framework, but it is through thought experiments, through the simple, powerful act of closing our eyes and envisioning space itself stretching, that these abstract concepts become a visceral, personal experience. This is the true magic of science. It doesn't just provide answers, it invites us on a journey of wonder, encouraging us to ask better questions and to find joy in the vast, vibrant unknown. Thank you for allowing me to guide you on this particular journey, for lending your curiosity and your imagination to one of the most profound mysteries of our existence. If this exploration has sparked a sense of wonder in you, please share that feeling. Pass this video along to someone else who looks up at the night sky and wonders what's really going on out there. And if you want to join me for more deep dives into the universe's greatest enigmas, from black holes to the multiverse, make sure to subscribe and hit the notification bell so you don't miss what's coming next. Our community of curious minds is what makes this channel so special. I'll leave you with this final thought. In a static, eternal universe, every moment might feel similar, interchangeable. But in an expanding cosmos, every single moment is truly unique. The universe is literally not the same as it was a second ago. It is larger, its story is longer, and the distribution of galaxies within it is more diffuse. We are not living on a fixed stage. We are participants in an ongoing, evolving narrative, a story that is still being written. So the next time you feel the weight of the everyday, remember that you are living at a unique coordinate in space-time, a singular point in an ever-growing, ever-changing cosmic story. And your ability to look up, to wonder, and to understand even a fragment of it is perhaps the most beautiful part of that story. Before you go, I have a couple of small but mighty requests that truly help this channel continue its journey through the cosmos. If this exploration of the expanding universe sparked a sense of wonder for you, please take a second to hit that like button and subscribe to the channel. It's the absolute best way to make sure you don't miss our next adventure. And while you're there, tap that notification bell. It's like signing up for a direct mission alert, so you're always in the loop when we drop a new video. Now, I want to hear from you. This thought experiment is a two-way street, and your perspective is a vital part of it. Scroll down to the comments and tell me, what part of this journey resonated with you the most? Was it the eerie feeling of imagining space stretching around you, the historical detective work of Hubble and LeMaitre, or the mind-bending mystery of dark energy? Maybe you have your own analogy for cosmic expansion that's even better than an inflating balloon. I'd love to hear it. Sharing your thoughts and questions down there is what transforms this from a monologue into a real conversation, building a community of curious minds all trying to grasp the universe's grandest secrets together. And if you're hungry for more mysteries, the journey is just beginning. In our next video, we'll be venturing into one of the most extreme and fascinating predictions of Einstein's theory of relativity, the incredible light-trapping enigmas known as black holes. We'll explore what happens at the very edge of a black hole's event horizon, wrestle with the paradoxes of what might lie at the singularity within, and even examine how these cosmic monsters might be our gateways to understanding the holographic principle. And after that, we'll dive headfirst into the provocative and thrilling world of multiverse theories, asking the ultimate question: is our universe just one page in an infinite book of cosmic possibilities? You won't want to miss it. From the bottom of my heart, thank you. Thank you for your time, for your incredible curiosity, and for choosing to spend this part of your day contemplating the profound and beautiful mysteries of the cosmos. It is a genuine privilege to get to explore these wonders with you, and I am so excited to continue this journey together, looking ever deeper into the fabric of reality. Until next time,